Yeah. All right, good morning, everybody. The first thing that I want to start with is this part of the PowerPoint because we had some issues with it last week. So I want to make sure that everybody's settled as far as this goes. So, and this redox reaction question, what ended up happening, the question did not even pertain to actual redox numbers being assigned. But one of my students was kind of bothered by the fact that the redox numbers, the oxidation numbers, when you assign them, don't really work out, or maybe don't work out the way you're used to. So on this reaction here, we take S4O6 2 minus, and we kind of split that up. We have 6 oxygens. Oxygen, except for in the case of peroxide, has an oxidation number of 2 minus. So this oxygen here, I have 6 of them, each of them being 2 minus. So 12 minus overall. And when you write this out, though, you can see that this compound has an overall charge of 2 minus. So that means that I'm going to have 2 extra minus signs if I make this little chart. Now that leaves me with 10 to assign for the positive charge on the sulfur, but I have 4 of them. And you're like, well, I can't have an oxidation number of 2.5, but you actually do. So I don't know how to draw 2.5 plus signs, but that's exactly what it is. Each of these 4 sulfurs has a 2.5 oxidation number on average, which is really weird. The question didn't even ask you to figure that out, but that's the issue. And so if you look to the S2O3 on the product side, we have 3 oxygens, still 2 extra minus signs when I make my little chart. And so the charge on sulfur goes from 2.5 plus to 2 plus. So it actually gets reduced, and so that's kind of weird, but that is the situation. We were struggling with this last time because, I haven't really seen a whole lot like this. I don't think you need to worry about that as far as, assigning a fractional oxidation number, but if you wondered what was going on, that's what was going on. As far as the rest of the question, do remember when you're building a half cell, the reaction with the largest reduction potential is the item that's going to be reduced, unless you're told otherwise. In this situation, you're told that you need this middle reaction to go through, and then we're looking for the oxidation to happen from one of these, and we talked about that last week. So anyway, wanted to make sure we were all clear on that before we moved on. Now, the last thing that we covered before we quit for the day, and I think that's a good way to put it, was calorimetry. So I'm going to kind of fast forward to the part that we left off on. It's not too much farther than this, at least I didn't feel like it was. We talked about all these heating and cooling curves, and we had ended, I think we had done this FRQ, and then we did this FRQ, and then we had left with heating curves. So I think this is where we need to pick up. Okay, so here's the deal. When you're looking at a heating or a cooling curve, first of all, make sure that you're aware that you're looking at a heating curve, which is this top one, or a cooling curve, which is the bottom one. Oops. So here's the deal. Why does that even matter? Well, if I'm looking at a heating curve, as I go and increase time and the temperature starts to increase and I change phases, entropy is going to be increasing. And this cooling curve, entropy is decreasing. And so oftentimes they'll connect it to that. You need to think to yourself, well, if I'm cooling it, it's obviously going to decrease entropy. So if you're not thinking, though, you may look at this leg of the heating curve in this situation and think, okay, entropy is increasing because it's boiling. But if you're not thinking about it, still this is going to be condensation instead of boiling, right? You're going backwards. And you may not think about, oh, okay, that's going to decrease entropy because I'm going from a gas to a liquid. So be careful there. Also, when you're looking at a heating or a cooling curve, the temperature kind of stalls out when you're melting or boiling, okay? Now, these phase changes from a solid to a liquid, you can do one of two things when you're heating a substance. You can either change the temperature or you can change the phase. So what's going to happen is energy is going to go into actually changing the temperature and increasing it, or energy is going to go into breaking intermolecular forces, whatever they may be. In this case, if it's it doesn't say what it is, but if it's boiling, water, we're going to take all of the enthalpy that's added, and it's going to go into breaking hydrogen bonds and London dispersion forces. So just be careful if you're asked to label what is actually happening. The flat parts are phase changes. And if you have 3 stages or phases of matter, you only have 2 of the flat legs here. So those are just some things to think about. If you're asked to do some calculations, heat transfer due to a temperature change, you can just use the same heat formula that we talked about last week with calorimetry. Now, if you have to do, like, for example, if the temperature changes and then you also have a phase change, you have to do 2 different problems, okay? The first problem will be the temperature change using this heat formula, but then also they will give you the energy needed to change the phase. So the enthalpy of, vaporization per mole. It'll be kilojoules per mole, and you'll have to actually add them. Now, be careful, right? If you're doing a cooling curve, those signs, as far as positive and negative, will be opposite. So let's say that you're given the enthalpy of vaporization, which would be right here. Well, if you're cooling, then that's actually that would be condensation. The enthalpy of vaporization would be a positive enthalpy because you're going to have to put energy into it to change the phase, right? Here, energy is going to be released. So that would be, take the same number and it'll have to be a negative enthalpy, right? So these are just some things that you know how to do it, but those are some tricky things that they may throw in there that if you're in a hurry, you may not think about it. So this is that point right here. Be careful because they'll give you one, and if you're going to a cooling curve, for example, instead of a heating curve, you'll just have to flip the sign because it's the same amount of energy, like absolute value of it, but it's going to be the opposite sign. So this work in pressure and change in volume, we talked about that a little bit last week. That goes along with pistons. I haven't seen that's more of a physics thing. It is in our learning objectives, but they haven't asked a lot of questions about it as far as using that formula. I could be wrong, but I don't think they've asked any questions about it. So anyway, this is a typical kind of multiple choice question about calorimetry. This is about the styrofoam cup. Please understand on an FRQ, always, the amount of energy absorbed by the styrofoam cup or whatever calorimeter type equipment you're using will always be able to be negated, which means that you won't have to calculate that in. Okay? But on the multiple choice, they will ask you conceptual based questions on, if you don't do the experiment correctly, if it's not covered, or what could happen if this or that happens, okay? So go ahead and take a look at this multiple choice question and pick a response, and we'll talk about it. It's a lot of reading, but take your time to eliminate things as you can. And when you're taking the test, take the time to actually write, on your test. You guys got it? Okay. So remember, on these multiple choice, you have about a minute and a half, right? So that wasn't quite a minute and a half, but it was pretty close. So this is one of those, it's almost like a brain teaser. You're like, wait a minute, what? And this would be where I would draw on my paper, maybe draw a little cup and think about it, right? I can't hold that much stuff in my head and then also read questions. Draw a picture. So what you guys got, did you all find that the answer was B? The value would be too small because the heat was lost to the surroundings. If you lose enthalpy to the surroundings, that energy will not be part of your data for your system, right? So the universe is the system plus the surroundings. So you're doing a calorimetry experiment, you really want to test that system out, right? What's happening in the system. If you lose energy to the surroundings, that's going to be enthalpy that's not going to be present in your data in the system. See what I mean? So any problems with that one? We talked a lot about this. Plus, we kind of messed up the calorimetry lab enough that, you're not going to get the right numbers. So it kind of goes well with that. All right, so the net change during reaction is the sum of the energy required to break the bonds. We did this like so many times, but I'm going to keep saying it. You got to think about a bond like two magnets stuck together, okay? If you want to pull those magnets apart, you're going to have to put positive energy into it, okay? If you have two magnets, you're holding them in your hands, and they really want to come together, right? And you let them come together, and you form a bond, basically, between those two magnets. Energy is going to be released. You're going to hear the magnets click. Okay, you're no longer going to feel that resistance as you try to pull them apart. So no matter what, you just need to think about breaking bonds takes energy. So basically, there's always going to be positive enthalpy put into the reactant side of an equation to break those bonds, and then energy is going to be released, right? Energy is going to be released when you form your bonds. Now, what ends up happening, the energy in the bonds of the reactants, if less energy, positive, put the energy into breaking those bonds, if less is needed to break the bonds than what is released when you make the products, you're going to have an exothermic reaction, right? So you got to kind of think about it like this. Like this is going to be, oops, I'm sorry. I had the pen going, but I didn't. Thank y'all. All right. So you have, let me try to hit that again. You have positive delta H going into breaking the bonds in the reactions, and then you're going to have negative enthalpy when you make the bonds in the products. So if this positive number is smaller than this negative number, once you sum up all the energy in the bonds, then you're going to have exothermic, right? Which is an exothermic reaction. Y'all know that is a negative delta H overall. So the negative numbers have to be bigger than the positive numbers to get a negative number when you add them together. Okay? Yes, ma'am?
So when you break bonds and form new ones, is it always a lower potential, or is that one for exothermic?
So this is exothermic. So endothermic, right? The enthalpy in the reactants, the energy needed to break the bonds in the reactants, could be larger than the energy released when you form the bonds in the products. In this case, the negative enthalpy is going to be less than the positive. Let me put a plus sign in there. So your overall reaction is going to be a positive delta H. So that's, and y'all know that when you're reading a multiple choice question and it gives you the enthalpy of the reaction, it's negative 42 kilojoules per mole. Well, you know that's exothermic, but this is graphically how you show that. Okay. So that's what I just said. And this is just one of those things. Now, when you're looking, now this is, here we go. Draw the Lewis structures, right? So you're going to have to, when you're doing all this math, you have to draw the Lewis structures, and they'll give you the bond enthalpies for a single bond, for a double bond, for a triple bond. Be careful. An oxygen, single bond oxygen is different than an oxygen double bond oxygen in the enthalpy. So you got to draw the Lewis structures. It's not worth losing all the points because you don't feel like drawing them, right? Whatever work you don't do now is work you're going to have to do if you have to take this again, later. So here is a good example of what that looks like. Answer the following questions that relate to the chemistry of nitrogen. Two nitrogen atoms can form a nitrogen molecule as represented by this following equation. Use the table of average bond energies below to determine the enthalpy change for the reaction. What's the bond enthalpy if you don't have a bond? Nothing. That's right. So don't let this one trip you out. two single nitrogen atoms won't have a bond, right? It'll just be that. And when you're drawing these, it may take you a little bit more time, but like in this situation, if just pretend that I had made 2 or 3 nitrogen molecules, I would actually, draw that out. And then that helps me to visualize what's going on. If you're in a rush, like, well, I don't have time, but to me, that's where I'm going to make my mistakes. So it's worth to me to invest my time. So anyway, a little trick, and for those diatomic, 7 molecules that you have: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. However many valence electrons, or how many bonds they typically make. For example, oxygen needs 2 valence electrons, so it's going to form 2 bonds. Like oxygen, diatomic oxygen has a double bond. Nitrogen needs to form 3 bonds, right? So nitrogen, and this, I'm using my lone pairs here. I'm not drawing everything. My pen doesn't really like to draw circles. But, so that is a quick little thing to do for your diatomics, because they're often involved in these reactions. Anyway, so if I'm just looking at this, right, this is, let me kind of erase that. So this is 0. But if this had actually been something that was in a bond, whatever number I had gotten would be a positive number, right? Because energy is going to be needed to break this bond. There are no bonds. And so over here, energy is going to be released. Whatever number this is, right, has to be a negative, because energy is going to be released when I form bonds. And then I'm just going to add them up. So 0 plus negative 950 is negative 950. Let's just pretend that I had something over here. It's not even shown, but let's just say, I don't know, the reaction had N. It did not have that, but let's just say it did, okay? If this had, that doesn't balance, but whatever. That balances. So let's just say you had that. This would be a positive 160 kilojoules per mole, all right? So I would take positive 160 and add it to negative 950, and it would still be an exothermic reaction, to the tune of, 690, yeah. So that's negative. All these things, I just draw a T-chart. Everything over here on the reactant side is positive, everything over here on the product side is negative, and whichever number's bigger, that's going to be the sign of your answer. So it helps if you kind of draw it out graphically. So there's it. 1 point for the correct sign, 1 point for magnitude. So that means that if you didn't know what we just said, and you put down positive 950, you'd only get 1 point, but that's really an easy point to get if you know what you're doing. All right, electrostatic forces. Just talked about this last week a lot. The stronger the intermolecular forces, higher boiling point, higher melting point. But vapor pressure is like the only one that's not higher if you have higher intermolecular forces. It actually is going to lower it. When we talk about vapor pressure, we have like a little closed container. If I just draw one somewhere, would help. What just happened? Oh, just like my computer had a little. So we just have a closed container, right, and a liquid in here. Maybe some acetone. It has a pretty high vapor pressure, which you know because when you open up fingernail polish. What that means is if I just have, if I have water, for example, the amount of water that will be in vapor form for this amount of a liquid, whatever a fixed volume is, well, maybe I may have this many molecules. But if I have something that has lower intermolecular forces like acetone, I would have more particles in vapor form in this closed container. And those particles, as they move around and hit the sides of that container, that is vapor pressure. So the lower intermolecular forces are going to allow more particles to vaporize inside this closed container. That's what that word means, okay? So thinking about, again, what are our intermolecular forces? We have dispersion. You're going to call those London dispersion forces. And so if we look at something like, we talked about this a little bit last week, iodine, bromine, chlorine, and fluorine. If you look at the periodic table, the one on the wall back there, fluorine and chlorine are gases at standard temperature, at 25 degrees Celsius at room temperature. Standard temperature pressure is 0 degrees Celsius, those aren't the same. But at room temperature, these are gases. This one's a liquid, that one's a solid. The reason why is because they have more London dispersion forces. As I go down the periodic table, there's more electrons, so it's more polarizable. Again, reminder to you, do not say it has anything to do with mass. It has a greater number of electrons, which makes it more polarizable, increases London dispersion forces. If you don't know anything else on that AP exam, I feel like you got that. Anyway, so that is, we can sit here and say, London dispersion forces are the weakest, but that's not always true. Sometimes when you have a big enough difference in the number of electrons, you can have something that's polar, right? And another substance that only has London dispersion forces. But if there's a big enough difference in the number of electrons, the London dispersion forces can be stronger than a dipole-dipole interaction. And you can tell that because they'll give you boiling point information, or they may give you vapor pressure information, and you can infer it, okay? So dipole-induced dipole. So what that ends up happening with that is you have something like HCl. So that would be, if I have a hydrogen chloride gas, and it's in a chamber with chlorine gas, okay, that HCl, which has, a positive dipole over here and a negative dipole over here, that's how you draw dipoles. Remember, try to make it 8, but don't close it up all the way. Anyway, when this comes in contact with a chlorine molecule, I'm running out of room, so I'm going to draw it smaller. It doesn't have a dipole, but the negative dipole on this chlorine, right, will induce a positive dipole on this chlorine, right? That makes sense? All right, so anyway, that's what that is. You have something polar and not polar, and they'll be, that's a little bit stronger than London dispersion forces. They don't bring that up a whole lot, to be honest with you. You have dipole-dipole, 2 polar molecules, so I have 2 HCl's. Yeah. And do remember, a hydrogen bond is just a very strong dipole-dipole interaction. That is actually what it is. So a hydrogen bond is where you have a little fun, F-O-N, right? And you have to make a sandwich. Y'all got that. I know you do. So if I'm looking down here, again, if you're looking for a hydrogen bond, I don't like that they drew this as, I guess they made it red. This intermolecular force is red. But let me kind of change my color here. I would like it, intramolecular bonds. If we make those a solid line, I think that will help you a little bit better. You're looking for a sandwich. The bread has to be a F over N, and there has to be a lone pair on one of them. So here's my lone pair, and that's where I'm going to have my intermolecular force, the hydrogen bond, and then there is an intramolecular bond between the other one. So we did that a lot. If you need to look back over that, that's on last week's video. All right, so here is FRQ practice. Structures of dimethyl ether and ethanol shown below. The normal boiling point of dimethyl ether is 250 degrees Kelvin, whereas the normal boiling point of ethanol is 351. So right there, you should already be thinking about, okay, which one has stronger intermolecular forces? Account for the difference in boiling points. You must discuss both of the substances in your answer, and they always say that. So you can't just talk about one, you have to talk about both substances. Even if you feel like you're repeating yourself and saying the opposite thing, you have to do that. Go. see a couple people still writing, so kind of wrap up what you're doing. Okay, so before we even answer the question, let's go ahead and look at this. Dimethyl ether. What happens here? You have a weak dipole on this. Let me wake my pen up a little bit. This oxygen and carbon bond here. So that is a little weak negative dipole. All right, oxygen carbon bonds are polar. Carbon hydrogen bonds are not. So heads up on that. Obviously, there we go. So there's your little negative dipole if we want to draw that in. Whee! Aw. There's the answer. Let me try that again. So there's your little negative dipole. And this is not going to be a linear shape. It's going to be kind of pointed down if you look at it. But here, if you count the number of electrons, they are very similar as far as polarizability. The ethanol has one less electron because it has one less hydrogen, so that's not a very big difference. You can tell already that the ethanol has a boiling point that's higher, and the reason for it is, you can form hydrogen bonds here because this oxygen has a lone pair, and then another ethanol, if you can kind of visualize it, I won't draw the whole thing, but it would be, this way. Like that. So it can form hydrogen bonds with itself. And don't talk about it forming hydrogen bonds with water. I mean, you can, but does it say it's a solution? No. It's just ethanol. So be careful there. I've seen that on some tests. So both of them have London dispersion forces. Ethanol, though, has the ability to form hydrogen bonds. So that's the big difference. If there are hydrogen bonds, you have to reference them. They're going to bring that up, okay? So, the weak dipole-dipole interaction, I just talked about that with dimethyl ether, wow. And then it has London dispersion forces, but then ethanol can form hydrogen bonds, okay? And that's all talked about right here. You get 1 point for recognizing that ethanol can form intermolecular hydrogen bonds, whereas dimethyl ether do not. And then 1 point is for recognizing the energy required to overcome the weaker intermolecular forces in liquid dimethyl ether. So more energy is required to overcome the stronger hydrogen bonds. So because they're talking about boiling point, if you didn't say, dimethyl ether has hydrogen bonds, so more energy is going to be needed to change that phase, then you only got 1 point. So you look at the question and what it's referencing to, because it's not just saying which one has stronger intermolecular forces. It's saying why does it have a higher boiling point. So you do need to talk about the energy to separate those liquid particles and make them gas particles. Because remember, there's always going to be, if you're looking at a heating curve, the highest enthalpy is going to be for vaporization, because you have to overcome all intermolecular forces, and that's a common question. So, inter versus intramolecular forces and chemical versus physical. In general, intermolecular forces are weaker than intramolecular forces. There's a common misconception that as you boil water, you make hydrogen and oxygen gas. But I promise you, your stove isn't giving you enough enthalpy to actually break the covalent bonds in water. The enthalpy needed for that is much higher than the enthalpy for vaporization. Right? So be careful there. We already talked about the relative strength. London dispersion forces are typically the weakest, but it can be quite strong if you have a very polarizable molecule. Dipole-dipole, then hydrogen bondings. Ion-dipole interactions are where if we try to, for example, dissolve salt. The sodium ion, as it's surrounded by water, that is an ion-dipole interaction, right? And so if you think about it, the ion-dipole interaction there, if it's actually stronger than the hydrogen bonds, for example, in water, that's why the boiling point of water that's in a solution is higher than just plain water. because the water molecules are stuck to those ions in a stronger force than the water just bonded to itself intermolecularly with hydrogen bonds. Okay? Covalent bonds and ionic bonds, that really depends on your Coulombic attraction present in your ionic bonds. You know, what's the charge, what's the distance on the ions. So anyway, already said this lots and lots of times. So high viscosity, I don't think you need to worry a whole lot about that. But viscosity is resistance to flow. So, you know, something like pancake syrup that's cold is very viscous, or lava. If you're not familiar with that word. Surface tension, so look, everything's high, right? If you have high intermolecular forces except for vapor pressure, it's the only one that's different. Alright, so if you're asked for ranking in order of melting point, boiling point, viscosity, surface tension, or vapor pressure, what they're actually asking you to do is rank them by strength of intermolecular forces, either increasing or decreasing. And then I'm going to really pay attention to whether they're asking me increasing or decreasing, and I'm going to, on my paper, make a list so I don't mess up. Okay, so look for molecules with hydrogen bonding. That's going to be the first thing that you should look for. Look for molecules with dipoles then, and that's kind of what I did, right? Larger molecules have stronger London dispersion forces because they have more electrons, so they're more polarizable. And so that's often going to be the deciding factor in those multiple choice questions. Whee! So again, intermolecular. I feel like that should say that's a type of intramolecular bond, right? Ooh, I didn't make this particular slide, and that actually looks like they took it from a textbook or something. I don't think a person made this, but that is super wrong. So this is an intramolecular bond. This right here is an intermolecular force. Intramolecular bond. So I wonder if no one caught that. So that's crazy. Yay! Ready to do an FRQ? You better be having it on Monday. Answer the following questions using the principle of molecular structure and intermolecular forces. So you got part A, 1, and 2 here. So good luck. I wish you well. I don't know if I'm just checking that, make sure everything's working. I got a little stall here. That's not where we're at. Uh-oh. What can I do for that? It looks like they turned it off or something. That's not good. It looks like the stream help is not good. I don't think I'm in charge of that. I actually on Wi-Fi. I'm hooked up to the Ethernet cord because I don't trust the Wi-Fi around here. I wonder if the county office is like, no stream. Oh, I fixed it. Yay! Yay! There we go. So let's go ahead and get this. Sorry for the stall there in the transmission. Should fix itself now. What? Well, they're just pulling from. That's okay. It's good practice. No, they're just these are actually they're the same, right? But they're pulling from release exams. These are both release exam questions, so they obviously like these questions. So that's not the worst thing that's ever happened to you, I don't think. Monday, like just cross your finger. Oh, Monday will be the worst thing that's ever happened to you. I feel like I don't. Let's see if I can get this to refresh itself. That's not changing. Ralph, you got any ideas? This screen seems to have stalled out on me.
Did you stop it already on the
Yeah, I stopped it and then.
OBS?
I'm sorry?
The program?
Yeah, I stopped it and then I restarted it. Like it says I'm streaming. But it's stuck here, right? It's like paused out, stalled out on this screen. So maybe I stop it and restart it.
Is that what you did last time?
I don't know.
Last time you did some of your work.
Wait, what was the question? Are you writing that?
I'm very right.
Actually, there we go. Alright, I fixed it. Sorry, home viewers, if you actually exist. Got a little stalled out there. Alright, you guys finished with this FRQ? No, ma'am. I like the politeness of that. Alright, I think we're back up and caught up to speed here.
In 6th grade,
So just going back to this question, someone in my class already noticed that these are the same molecules. Well, that's okay if you can see that this is a real FRQ and the other one is a real FRQ. And so the fact that they're the same, great. Like you'll be ready because they obviously use these a lot. And any type of, if it ends in OL, you know, it's going to be an alcohol and it's going to be able to hydrogen bond. So even if it's not this alcohol, you know, if it was methanol, if it was butanol or whatever, it's going to have that same hydrogen bonding there. So we went over that, talked about IMFs again, and then here we are on this FRQ. So when we start looking at this data, we can see that the boiling point here is much less for C2H6O than C2H6O. So I don't know if these are they exactly the same as the last ones? That's awesome. All right, great. So here's box X. When you draw Lewis dot diagrams, like maybe these are easy because you just saw the molecule. That's great. I'm happy for you, but you need to take the time when you're doing this and, you know, count up your valence electrons. So if I'm doing completely Lewis dot for the molecule in box X, so if I have C2, I'm only counting, do I not know how to count? 1, 2, 3, 4, 5. Yeah, that is 6. Whatever. I was like, I only see 5. Whatever. Thank you guys for not judging me. This is going to be 4 times 2, which is 8 valence electrons. This is 6, and this is 6. So overall, in my picture, when I'm done, I need to have 20 valence electrons. Okay. When you draw Lewis structures, what you need to do, first of all, is give yourself a single bond between the central atom, and in this case, you don't have a single central atom, you can have a chain here. But a single bond between the central atoms and the terminal atoms, okay? So let's go ahead and do that. So when I draw these bonds here, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 times 2. So I have 16 electrons, you know, showing here. The next thing, you know, just to refresh your memory on the steps, even if you got this done and it was easy, any extra electrons are going to go on the central atom. Now, if I look at these carbons here, they already have a full octet, so I'm not going to put any there. The only atom in this picture that doesn't have a full octet is going to be my oxygen. So those extra electrons, those 4 that are not in the picture here, sorry, I'm trying to draw a circle and my pen doesn't like to draw circles, so that's the best I can do, I think. So now I have 20 electrons, and if you want to, this is a really good time, even though it's not necessary, to review formal charge, right? So formal charge, when you want to check your formal charge, maybe the Lewis structure you have to draw is not that easy. if you're asked what's a formal charge on something, you also need to know how to do it. So formal charge is going to be the number of valence electrons in an atom just by looking at the periodic table. So for example, on carbon here, the number of valence electrons is 4, and then you minus 6 in berries. Do you remember me telling you that?
Yeah.
So look, there's 1, 2, 3, 4, 6, minus 6, you have 4. On the oxygen, the valence electrons for oxygen are 6. Then I'm going to count each berry. 1, 2, 3, 4, 5, 6. So the formal charge on the oxygen is also 0. I believe that the formal charge on everything is 0, which is cool. If you have a polyatomic ion, and let's say we have, I don't know, nitrate, the formal charge on one of those is going to have to be -1, right? That's how that works. Is that ringing a bell on formal charge? Like, I'm just trying to hit everything I can to help you out. So the rest of it should have been pretty straightforward. If we kind of look at that. So there was A, and then the key for A is just right here. And you know, I just filled in. Yeah, that's box X, which is kind of what I did. On box Y, you had to draw the other one. So there is the what was it? Dimethyl ether, which is I think this is acetone. So, but there's the other one, and we just saw that, so no worries. Let's go ahead and we haven't done this one yet. I feel like we looked at something that looked like this last week. Was it exactly the same question that we looked at last week? No, but it was the same molecule, so you start to see a theme here. So this is not a waste of time. So go ahead and do C and D, and then we'll talk about it. Notice again they have that each underlined, right? So you make sure you're referencing both. And this question is asking about boiling point. No, it's just asking about intermolecular forces, so you don't actually need to reference, the amount of enthalpy needed to, break intermolecular forces or anything like that. Read those questions really carefully. All right. Y'all are intermolecular forces champions. I wish you well on this. Maybe the whole time. It won't be. I'm just kidding. That would be cool though. I see a couple people finishing up tea, which is fine. Alright, so let's go ahead and talk about this. Dichloromethane has greater solubility in water than carbon tetrachloride has. Alright, so carbon tetrachloride is completely nonpolar, even though it has polar bonds between the carbon and chlorine. Overall, there's no net dipole because it's symmetrical and they cancel out. That's not true with dichloromethane. We talked about that specifically, those two molecules last week. So I'm thinking maybe what we did last week, maybe did like parts A and B, and this is C and D. I think that might be the issue. Anyway, so when you go ahead, whoops, it's right here. When you go ahead and look at the answers here, that's the bottom two right here. So CH2, Cl2 is polar. I already just talked about that. And so the CH2, Cl2 will be able to have dipole-dipole interactions. Will it have hydrogen bonding with water? No, there's no nitrogen, oxygen, or fluorine. So no. So be careful there. Not everything has hydrogen bonds. Let's see, or LD, yeah. And it also interacts with LDFs. So both of them do. Anyway, CH2Cl2 has a higher vapor pressure because the combination of LDFs and dipole-dipole forces in CH2Cl2 would be weaker than the strong LDFs in CCl4. And that's what I was talking about. If you have a big enough difference in polarizability because of the number of electrons, that could happen.
Do we need to list London dispersion forces that have something that's like stronger? Like it has like dipole forces. Do we need like
Yeah. Do you always need to talk about London dispersion forces? Yes. Okay. So if it has hydrogen, basically you need to talk about whatever intermolecular forces are present, whatever they may be. You need to reference them all. The keys will always go in hydrogen bonding if they're there, and that'll be a point. And then London dispersion forces come up. So if we're comparing, which they're asking you to do, intermolecular forces, they both have that. So when you make that comparison, you need to reference it. IMF forces in biological and large molecules. So the thing about this, they haven't asked about it a whole lot on the AP exam yet, but you never know. Like, there's rolling stuff out, so you got to be ready. It is a learning objective that you're able to identify the non-covalent interactions within and between large molecules and connect them to the shape and the function of the large molecule to the pressure and magnitude of these interactions. So, anyway, what ends up happening here, we have those weak intermolecular forces between molecules. And we already talked about, there are hydrogen bonds in DNA, right? That's what holds together those nitrogen base pairs. Did you hear what I said? Nitrogen base pairs. Yes, there you go. If you had to actually break, like, all of those covalent bonds, if they were covalently bonded when you unzip them and do transcription, that would be a huge amount of enthalpy needed versus the enthalpy needed to break that intermolecular. It's just kind of cool, right? I like it. Anyway, you have dipole-dipole interactions and you have London dispersion forces. So, if we look here, there's ionic bonds holding it, disulfide bonds. Do you need to know disulfide bond? No. But ionic bond, if you saw something like NH3+, which, don't let that freak you out. Usually we talk about NH4+. Look, it's got a positive charge and the oxygen has a negative charge. So there's an ionic bond there. So if you were asked to say, what kind of bond there, get a positive and a negative ion, like certainly you would say ionic bond. Disulfide, I don't think that would be a thing. This is a biology concept, hydrophobic interactions. Basically, what this would be in terms of chemistry on AP chemistry exam, what you have here is you have nonpolar ends of a little biological molecule, and so the only interaction they're going to have there are London dispersion forces. So, whatever. What ends up happening, here we just see this cooling around so that you have these things interacting. There's like, in biology, they'll talk about hydrophobic and hydrophilic and how the hydrophilic parts will kind of gather together in the hydrophobic parts. But that's more of a biology thing, so we'll see, okay? But you can see here, there's your hydrogen bonds. There's your nitrogen, and then it's and a hydrogen bond with that. Not the hydrogen here. Oh no, the hydrogen here. There's the nitrogen. Sorry. Anyway, if we look, we can kind of like mix these up and put them in the right blank. So here, all you have is London dispersion forces. So that would be hydrophobic, right? If I put this in water, is it going to dissolve? No, because the weak London. This is the AP chemistry connection. The weak London dispersion forces found in this biological molecule or this part of this biological molecule will not be able to overcome the strong hydrogen bonds in water to be able to be dissolved in it. That's how you get to say that. So here you can see that's a hydrogen bond disulfide, and that's ion. I mean, we haven't really seen how this plays out on the exam because it hasn't played out on the exam yet, but that's what you got. So that's not a big deal, right? Entropy. So entropy changes that result in a positive entropy. So how when entropy or delta S is positive, you got to think about a couple things. And don't say chaos, that's not really going to help you. But entropy, when you have more moles, you have more particles, so there is a higher variability in the possible location of the molecules or the particles in that system, right? There's a higher number of possible arrangements. That's what it is. Like, that's the right answer, not chaos. There's more chaos. There's a higher number of possible arrangements of the particles in the system. Because if I have two particles floating around in a sealed vessel with a constant pressure, they always do that. I don't know where they get those sealed vessels with constant pressures where they can heat them to 492 degrees Kelvin. I wish those students will. But when we're talking about that, if I have two, the possible arrangements of those two in that volume will be less than if I had 7, right? That's the idea. Increasing the volume, they have more, they're going to have a larger space to which they can arrange themselves, so there's more possible arrangements of the particles. Solid to a liquid or liquid to gas, and so we talked about that with the heat curve already, right? I feel like I already hit that for you. Forming more complicated molecules. So you have more moles of electrons. The more complicated molecules, that's a little bit subjective. You also need to look at the phases and stuff. I wouldn't lose sleep too much over that. In this situation, check it out. I'm starting with 1 mole of a gas and I'm going to 2 moles. So that's a positive entropy. And then here I'm going from a liquid to 2 gases. So that's positive entropy as well. So here's a nice picture that shows you that. And you can see again the number of possible arrangements as I change phases increases. And so that's the idea. And I kind of wish I had said that. That's the magic words for you if you need those. Yay! FRQ. There's a lot of practice today, which is really good. Everybody's like, I hate this for you. The combustion of carbon monoxide is represented by the equation above. Determine the value of the standard enthalpy change for the combustion of carbon monoxide at 298 using this information. It's just asking for entropy, right? So entropy is going to be in joules. Now, sometimes when you do like your Gibbs free energy calculations, you'll have to have entropy and enthalpy. And so be careful because those will be given to you in kilojoules, so you'll need to convert. Remember that? But enthalpy of a reaction is always kilojoules per mole. Entropy is the only one that's just joules, so you need to be careful there. Okay. Did you guys figure out that you can use the formula on the formula sheet for this? Yeah? No? Just do it? So if you're struggling, take a look. This is a good thing to be really mindful of, okay? If you look on the formula sheet, there are three kind of little sigma-looking formulas. There's one for enthalpy, entropy, and Gibbs free energy. And notice that it says the entropy of the products minus the entropy of the reactants. Does it say the entropy of formation or anything? No. So the other ones, if you're going to use this formula, like the same style formula for Gibbs free energy or enthalpy, you have to be given the enthalpy of formation. See that little F? All right, so this does not fly for all kinds of reactions like this. If you're doing this style of formula for entropy, you don't have to have the entropy of formation. That's not a thing, okay? But in this situation, so the enthalpy of formation and the Gibbs free energy of formation of the products minus reaction, you have to make sure that it's that kind of information, you know. So be careful. So you just really had to plug this into the little formula. You got it? All right. So notice here, it's just the entropy of the products. Right, products go first, minus the sum of the entropy of the reactants. And notice here, because this is per mole, right? In the balanced equation, you only have a half of a mole of oxygen. So you have to multiply the entropy of oxygen by half and then add it up. So did you guys get that correct? And like I said, entropy is in joules, right? So if you do this work, you don't change it to kilojoules. Like I said, when you put this into formulas with enthalpy or Gibbs free energy, you would need to change it to kilojoules. But in this situation, it's not needed, right? All right. So talking about the formulas for Gibbs free energy and enthalpy and temperature. This is the one, and notice, please don't say spontaneous and non-spontaneous. What they're doing here is they are using old sources. You need to say thermodynamically favorable. It's been a hot minute. That's supposed to be funny. It's been a hot minute since I've said thermodynamically favorable. I think it can make a little fun, like thermodynamically favorable. It could be a song. Just kidding. Anyway, you can actually use this formula if you're given data. If you're not given data and you're asked about entropy, first of all, you can look and see, are you making more gas? Are you making more particles? That kind of stuff. But then it may ask you about, is this thermodynamically favorable at high temperatures, low temperatures, whatever, right? And so that's where our little smiley face man comes together, and I'll show you that, okay? Anyway, notice this is what I was just telling you like 7 times, okay? You have to change entropy to kilojoules because everything else is kilojoules. So that last answer, I don't remember what it was. It's like 50-something, 80-something. I don't even know. So it would be 0.0 whatever the answer was, because you'd have to change it to kilojoules. Do y'all need to see the happy face men? All right, let's do it. I'm gonna have to go. I'll have to go to my little. I have to exit out of this. There we go. 1 second. Working on it. I don't have enough room here to draw the smiley face for you. Oh gosh. So this is how Kenneth gets crushed, if you wanted to know. Let's get particulate modeling. It's good. So I'll just make that go away. All right, check it out. When you're given a chemical reaction and you're asked, is this thermodynamically favorable or not, you'll be given the enthalpy and the entropy, and then you can look at it. So remember when you do the happy face man little thing that I'm about to draw, S starts with S, so start with S. Drew's laughing. That was the funniest day of my life last year, by the way. All right, so what you're going to do is you're going to go, if this is, and that's your change in entropy, if it is greater than 0, right? Let's just start with them both. Let's start with the enthalpy being negative. So if your entropy is positive, that means, you know, you're making more particles, you're making gas, whatever. That is something, you know, entropy does want to sort of increase in the universe. That's the second law of thermodynamics, right? Okay, so entropy has a tendency to increase in the universe. And then also, when we're looking at reactions, they're going to react in a way to lower the energy of the system. So this is always thermodynamically favorable. But if you want to, you can draw little happy faces. And entropy walks into a bar. I mean, when I say bar, I mean like a barbell. And then I go to the gym a lot. And then, you know, makes eye contact with enthalpy, and they just fall madly in love. And this is always, wink wink, thermodynamically favorable. Always start with this. If you don't start with this, it won't work. So anyway, well, let's do another situation. If our entropy is, you know, negative, and then our enthalpy is positive, so endothermic, and then entropy decreases, like entropy is not increasing in the universe, and nothing moves to a lower energy state. So this is never, so they're like not looking at each other. They never fall in love. Never thermodynamically favorable. Okay? So the other two, let's make our entropy negative, and let's make our enthalpy negative as well. So in this situation, like enthalpy is checking out entropy. Entropy may not look back at enthalpy. So like maybe they may fall in love. But so the way you do this, they're going to ask like a what temperature. So do you see how the little inequality sign, the little side is pointed to the H? So this is going to be thermodynamically favorable at low temps. Because temperature is a measurement of average kinetic energy, which is related to enthalpy, which is heat. Okay, I'm out. So the opposite of that, where this is positive, so enthalpy is checking out entropy. Enthalpy is checking out entropy. I wish these words just sounded a little bit more similar, but they, yeah, anyway. That would be just super. So this is only thermodynamically favorable at, and so the inequality sign is pointing, the big side is pointing to H, at high temperatures. Feel good about your life now? Okay, good. Let me go back to the PowerPoint. Whee! I say that. I don't know if I mean it. Oh, I found it. That's surprising. So if I'm taking the multiple choice test, I'm going to take it just a second. They're going to give you the data for the enthalpy and the data for the entropy, and just if one's negative, one's positive, I'm going to draw my happy face in, and then I'm going to make my decision. And now some of them are easy. If the entropy is positive and the enthalpy is negative, that's always thermodynamically favorable, which should already be in your head. So heads up on that. Oh, for your final, yeah. Like, I'm going to get done with this first. I feel like at the end we'll have some time to do that. It's like, Okay, so that's what we just did, and I already told you this like 4 times. So moving on with our lives. So how can you calculate Gibbs free energy? Here's the deal. Before you even talk about Gibbs free energy, you have to understand that this is the ability of a system to do work, and you got to think about, can work be put out into the outside of the system, right? So Gibbs free energy has to be negative for the system to do work, and for something to happen without outside intervention, which means spontaneously, Gibbs free energy has to be negative, okay? If Gibbs free energy is positive, you're going to have to couple a reaction to make it work. What I mean by that is you'll have to pair it up with something that has a higher negative, or a greater negative Gibbs free energy value. Do you recall that? I think couple in here in a minute, but I just want to go ahead and say that. So Gibbs free energy, if you look on your formula sheet, there's 3 formulas for Gibbs. Actually, there's 4 formulas for Gibbs free energy. So you have the first one where Gibbs free energy is equal to the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. So that was kind of what we already did. That's only useful if you're given the Gibbs free energy of formation. If it just says Gibbs free energy and it doesn't say formation, you can't use it, okay? Anyway, the next one is the enthalpy minus the temperature. Temperature has to be Kelvin. The only time temperatures don't have to be Kelvin is calorimetry. Always go to Kelvin. Anyway, minus the temperature times the entropy. In that situation, you got to change entropy to kilojoules. Then the next one is negative RT, and the gas constant that you're going to use is the first one that's listed. It's that 8.314. Don't pick the wrong R. Okay. And then the natural log of K. So this is where we're going to relate Gibbs free energy to the equilibrium constant. Equilibrium constant, for example, is large. Then Gibbs free energy will be negative and have a large magnitude. Okay, and then the last one is for electrical cell potential. That is negative N. N is the number of moles of electrons. So you know how that first one I did at the beginning of this review session, that one that I had written out, the S406 and all that, that was 2 electrons transferred for that reaction. Okay, so that N right there is 2. You have to balance. You have to put the 2 half reactions together and balance the number of electrons before you put it into here. So then F is Faraday's constant, and I feel like, yeah, it's given to you over there on the side, and E is the electrical cell potential. So there's your options. So there's what you have to work with. I don't like that it has no F here. It should. Better say formation. So Gibbs free energy, if it's negative, the electrical cell potential will be positive. So you have basically about a galvanic cell or a battery that can do work. It's not dead yet. Dead is at 0. Anyway, equilibrium constant will be large and greater than 1 really. Gibbs free energy, if it is positive and the electrical cell potential is negative, K will be less than 1. And then if it's at equilibrium, no change will be occurring, because the rate of the forward and the reverse reactions have come to be equal. So no net reaction, electrical cell potential has to be 0. And that's why when we get to galvanic cells here in a minute, if it asks you how could you increase the voltage, you cannot refer to Le Chatelier because electrical cell potential has to be 0 to be at equilibrium. And if your cell potential is 1.2 volts or whatever, you can't talk about Le Chatelier, and we'll go into that. It's a Q versus K argument, which the one in class we did with Q versus K, and y'all were like, we don't need to do that. If you put larger numbers in it, like I said, you get a different answer. So you need to do that if you're not at equilibrium. Q versus K is the answer. They really like that a lot because people really don't know how to do it, and so they'll pull that out. Anyway, coupling reactions. I just told you about this. So let's just say, I'll give you some numbers. I like numbers. I'm sorry. I don't know what I did. Baby, come back. Any kind of fool would see. I hit a button and I'm sorry. I'm singing. That's how tired I am. And I just can't live without you. I am hot. But if I walk over there to change the air conditioner, can you hear me talking? No. So you push the button and hope for the best. I have been told I'm hot. No, I'm just kidding. That's not funny. I didn't say that. I didn't say that. Push the button, Nicole. You know what? No. All right. What I was saying a minute ago, before my stuff disappeared. I think I got it. There we go. Let's just pretend that the Gibbs free energy for this one was, I don't know, 42 or 4.2. Let's just go with that. Kilojoules per mole of reaction. Positive. That is not going to happen all by itself. So it has to be coupled with another reaction. Let's say the Gibbs free energy of this one, right, is negative 7.3 kilojoules per mole. So if they get coupled, the overall process can occur. I think this is the situation with, I think it's photosynthesis. It has a coupling mechanism. It's pretty interesting. You can look at, this happens a lot with biology, right? So your little body, entropy is decreasing every day. Like, that's why you're alive. When entropy starts to decrease, So there's a lot of coupling in biological processes. Oh, look, here's an example of what I was just talking about. Let me draw one first, though. So this gives free energy is 0, and this one's negative 16.7 kilojoules per mole. So these are some enzyme reactions for creating ATP. And so that's when you're breaking down glucose for energy. Yay! So they have to go together. The sum of the free energy for the two reactions gives a negative, overall negative, I just said that twice, gives free energy, which is thermodynamically favorable, right? So I don't think I need to talk about Robin Hood, so there. Two reactions are said to be coupled when the product of one of them is the reactant of another one. So this product being the reactant for this one, that's they're coupled. It's not just like two random reactions that are just like having a party in a cell. Like the products of one are the reactants of another. So they're definitely like literally coupled. That one is creating the other one. So reactions can be coupled together if they share a common intermediate. And that intermediate is that middle step. And we already talked about that. I think we're good there. So here is a FRQ, yay! For reaction X, we closed the back door. I think the air came on. For reaction X, will the equilibrium constant Kp, this is pressure, yay, increase, decrease. When you have Kp, you have to use parentheses instead of brackets, right? Okay, cool. We're going to be using ATMs, probably. I don't think that even matters. Increase, decrease, or remain the same if temperatures rise above 298. Justify your answers. So you actually have data. When you actually have data, and you have some stuff and you're comparing it, you have to kind of weigh, do I need to use a formula here or not? If it's an FRQ, you're probably about to do some math, right? Yeah. And you can use a calculator since it's an FRQ. We did the You may be able to eyeball it and not use a formula. Got it? Did you choose math or no?
No.
No math. I see some boards with no work on them. You still thinking about it?
Yes.
Okay. If you draw happy faces on your page to help you with stuff, like that's not going to be an acceptable justification on an FRQ. It'll help get you going the right direction, but that's not going to be like, you're not going to get the points for just doing that, okay? If it helps you, I'll just kind of go ahead and draw those up here. I don't know what that little white show over there is, but whatever. So it's just talking about reaction X. Do you see how this is part B? Like if you were looking at Y and Z, I mean, that ain't helping you, right? So focus on what they're asking. So in this situation, and I'm gonna start with S. because you have to, let's see, it's positive, then your delta H. It's also positive. So it's giving you this thermodynamics when we're talking about standard temperature and pressure. It's 1 atm at 25 degrees Celsius, which is 298 degrees. Okay. So anyway, we can see here that this is only thermodynamically favorable at high temperatures. And the way you would justify that is you could say because the enthalpy is positive, but the entropy is also positive. This reaction will only be thermodynamically favorable and have a negative Gibbs free energy at high temperatures. Like you just say it out loud. You can draw your little smiley face man, but that's what you're gonna say. So if the Gibbs free energy is positive, that's not thermodynamically favorable, which means you'll have a equilibrium constant less than 1. Okay? So the equilibrium constant, if you raise the temperature, it's becoming more thermodynamically favorable, which will increase your equilibrium constant. If this messes you up and you're like, ooh, I can't do this in my head, write that down. Like write down if the equilibrium constant is, in this situation, if it's less than 1, right? I said 1 and wrote 0. And then your Gibbs free energy, it's going to have to be positive, and your we're not using electrical cell potential. Yes, ma'am.
Can you do the thing where you put like you added heat to the one side that it needs heat or energy or whatever?
Because of the.
Would that just be looking at
Since it's endothermic, right?
Yeah.
like could you just negate?
Here's the thing. What you're doing, you're talking just about enthalpy, but to be able to make a conclusion for the equilibrium constant, enthalpy is not related directly to the equilibrium constant. I mean, you can look at the formula and tell that equilibrium constant is directly related to the Gibbs free energy. Look at the formula. Gibbs free energy is equal to negative RT ln K. Does it have an H in there? No. So you have to find or think about Gibbs free energy and then make your inferences about K. You have to look at the whole picture. And you can tell you have to look at the whole picture because they've given you data on all of that. So let's kind of look at what they got. They did both ways. They did mathematically and without. So Kp will increase. If the reaction is increased for an endothermic reaction, then Le Chatelier's principle, the reaction will shift toward the products. There, is this what you were talking about? Okay, that does work. What year was, I don't know if they had the year on this. Okay, so this was before the redesign. After the redesign, if you say that, you better say Q is less than K. Even if you're like, what is that even, what am I even talking about? No, darn it. You know that Q is your reaction quotient, right? I don't know what I just did, but I'm sorry I did it. This is where we were. We're going to take a break, after this, so I'll just leave it at this screen. Is that? No. I'm doubting my life. No, it's okay. I'm not really doubting my life.
What is it?
It's okay. Everything's fine. I don't know what I'm doing when I push the button for the pin, but things happen. This is where we were, yeah? Yeah. Okay, and here's the answer. So in this situation, let me try this pen. Maybe it won't be so mean to me. In this situation, you can use Le Chatelier's principle and think, okay, it's going to shift towards the product side. But in that situation, Q on a number line is less than K. If you are talking with math, you need to say that. You need to say Q is less than K. This is an older one. The stuff that I said would be more for the updated curriculum, which is right? So be careful. Pretty much talking and reading other people's posts about this and equilibrium, if it's a free response and you're talking about Le Chatelier, you have to make the Q versus K argument. You can use your intuition and say, if I increase the heat, it will shift toward, I don't know what y'all are saying. You increase the
Or
temperature.
we put
Oh,
heat
because
on
it's
the-
endothermic?
yeah.
Okay. So what you were thinking was, heat is over here, so if it increased heat, it's gonna shift to the product side. That's good. But then you would need to take that extra step that Q is, less than K. If it was shifted back to the reactant side and you did that intuitively,
So,
then you would say Q is greater than K.
You would just say those.
because
no
you can't calculate Q in this.
Doesn't
but
matter.
It doesn't matter.
Okay.
Like, it's just, look, it's just one of them things. I'm serious, yes.
If you were to do it using the formula,
Right.
should I just, instead of saying like all that stuff down there, can I just throw in, make like an example of a temperature increase?
And I'm pretty sure, I mean, I had the key right there, I could have just said this, but what I said would be appropriate. Yes,
I think you said this, but if it was exothermic, it would be Q is greater than
if it's exo,
Well,
If-
I'm asking is that.
like if we could go up here and say the enthalpy was negative 131, and then if, so you're giving me a, for instance, if it was like that, and you added heat, or you increased the temperature, then it would just, yeah. Then it's Q, you know it's gonna shift toward the reactance of Q is greater than K.
Okay.
Just number one, think about it. But yeah, if you're talking about Le Chatelier and response, you need to talk about that, yes.
Wait, so you can just do the formula?
Yes.
Not having, I didn't have the RT, LNG, but I just had that.
I really think like what I said would be acceptable, because it just says one point is on for the appropriate justification, and I've seen on the newer ones what like things that I said that works. Yes,
Alright, so Q is like the constant state, or the present
Q
state.
is the present state, which may or may not be at equilibrium. Q is equal to K or at equilibrium.
Okay.
But if you know that if you increase the temperature due to Le Chatelier, look, it doesn't help you to say a dead man's name. It does not help you. Don't waste your time writing Le Chatelier. Like, it doesn't help you. Write Q versus K. Alright? Thank you for your work and learning how the universe works, Le Chatelier. But still don't say his name. It doesn't help you. Alright, so we made it through that. I think it's time for a break. You guys are looking a little bit already. Thank you. Thank you so much. I'm going to hit the mute button. All right, so let's get back to it. Yay! So we just talked about coupling of reactions. Little refresher for you here. The equilibrium constant. If you couple reactions, which means you combine them. I wish they would have said combining them. Do you remember when we did this and we talked about how the equilibrium constant is actually you can just look at the formula sheet, but it's going to be, A plus B, and let's just add some coefficients so we can, see it. Gives you C plus, 3D. Why not? That sounds good. Sounds like a fun movie. When we're looking at this, and we're writing the equilibrium constant, K is going to be equal to the concentration of the products raised to the power of their coefficients. I feel like I've said that enough times in my life that it should be my epitaph. And then the concentration of the reactants to the products. So, when you combine two reactions, what's going to happen, like here, for example, if I end up with 4 A's, if I combine reactions and I add them together, I cannot just multiply the equilibrium constant by 2 because that 2 is not times 2 in this reaction when I write it out for the when I write out the equilibrium expression for this reaction. That becomes a 4. You see what I'm saying? So what you have to do is if you combine or put reactions together, you are going to have to multiply by a factor or reverse the reaction. Okay, so when you end up doing that, if you multiply, like if I multiply this times 2, right? That gets raised to a power of 4 now. So you got to raise K, you got to square it. See what I'm saying? So if I take, and this gets multiplied by 2, if K was, 1.0 times 10 to the negative third, I actually have to square that, which remember, to the second power. When I raise a power to a power, you multiply the exponents. So the new equilibrium constant will be 1.0 times 10 to the negative 6. How you feeling? So when you multiply by 2, it's not like enthalpy or Gibbs free energy where you just multiply those values by 2. You actually don't raise it to that power because the coefficients are exponents. It makes sense if you think about it. Anyway, if you reverse the reaction, what you're going to have to do here, now my denominator is my numerator. If I reverse the reaction, and actually it's C plus 3D gives me 2A plus B, then the top of this fraction is the bottom of the fraction, and the bottom is the top. So you actually need to take the inverse of K, because you flip the fraction upside down. So now it's 1 over K. So if I reverse the reaction, it's 1 over this, and I'll solve for K. Okay? You don't just change the sign. Oh, now it's negative. You're going to have a negative equilibrium constant? No, that doesn't even make sense. So anyway, if you add reactions together, you're going to multiply the values, add the values, add the values. So if I had 2 reactions, like if I had another one written over here, and I combined them, you would multiply their K's. So that's how to do that. Ready to practice? Yay! This is very intuitive, but if you're not thinking, you'll get it confused with what you do for enthalpy or Gibbs free energy, for example. All right, so here's an example of it. Before you do your, there's a FRQ that has a little bit of this in it. So if I have this 2-step process here, and then the K, the equilibrium expression for this first reaction is given to us, and then here is the equilibrium expression for the second one, and determine the equation for the overall process. So if I determine the equation for the overall process, you can see that NO2 is a intermediate. It's not a catalyst because it wasn't present at the beginning and the end. So if it's formed in the middle of a reaction and used up, that's called an intermediate. So the overall reaction, when you're writing it, once you combine them, your balance equation should not have intermediates in it, and it shouldn't have catalysts in it, right? Because those will always cancel out. Just reminding you of that. Anyway, what is the equilibrium constant for the overall process? Well, here's the first process, here's the second process, and you actually multiply them together. When you multiply them together, you can see that that intermediate cross cancels. So it works out mathematically. But if you're given the values, like KEQ right here is 3, now it's 2, then of the overall reaction is 6, right? So this takes those elementary steps that we talked about with kinetics, if you're given elementary steps, but you're also given the equilibrium expression, which they don't, that may not show up together like that, but just to refer back to something you understand, you could multiply the equilibrium constants together. Okay? Do you see how that works? Okay, so for Gibbs free energy though, if you have enthalpy or Gibbs free energy, then you just start adding them. Because the Gibbs free energy is, for that reaction, there's not some fraction with coefficients and powers involved, it's just a number, right? You reverse it, you change the sign. That's not how it works with equilibrium, because equilibrium constant, again, is this ratio with powers and things. There we go. Thermodynamically favorable. So talking about kinetics, which I just kind of referred to, kinetics tell you how fast a reaction will proceed. Equilibrium tells you how far it proceeds, and thermodynamics tells you whether or not the system or the reaction is favorable at a given temperature. A reaction that is thermodynamically favorable will form more products at equilibrium, but it may be so slow that fewer products form in a reasonable amount of time. So, for example, iron rusting is thermodynamically favorable. It will happen without outside intervention. But if I get a bicycle and I start staring at it, waiting for that iron to rust, I'm going to be here for a minute, right? So the kinetics, the rate there is not very high, but it is going to have a negative Gibbs free energy and a positive K value. And that magnitude of K, if it's 2 times 10 to the 15th, that's a very large K, that does not tell you anything about how fast that goes. It just means when it's done, products will be heavily favored. Kinetics, equilibrium, and thermodynamic favorability, they all have their separate meanings, and they're not really related to each other. You have to understand what each little chunk means. Just because you have a high K doesn't mean it goes fast, and it doesn't mean, K and Gibbs free energy, you can have a formula for that. But as far as the rate, no. If you look at your Gibbs free energy formulas, is kinetics even in there? No. Okay, so I feel like we did this about a couple times today. Can't hurt. Gibbs free energy is equal to, I feel like, when you look, I'm down my life real quick. Oh, here we go. This is really what we're looking for on the formula sheet, so don't let that freak you out. Thermodynamic favorability means a reaction is product favored at a given temperature. I feel like we've done this so many times today, and Gibbs free energy is negative. You got it? Doesn't tell you anything about the rate. As K decreases, Gibbs free energy becomes more positive. Whatever. Okay, so here is the relationship between Gibbs free energy and equilibrium constant at 298 degrees Kelvin. So if the Gibbs free energy here is very large and very positive, you can see how small the equilibrium constant is. There's essentially no forward reaction. If Gibbs free energy is 0, you have to think about this, okay? When you're doing this work here, it's like really tempting to say, when Gibbs free energy is 0, K is also 0. No. When something's at equilibrium, K equals 1. Gibbs free energy is 0. Be careful. Okay? And so you can see here with a large magnitude negative number for the Gibbs free energy. Notice I'm not saying large and negative. That is oxymoron. A large magnitude negative number. I mean, I don't know if that would be an issue, but a large number is not a very large negative number. That doesn't know how the math works. Okay, so anyway, I have a very large KEQ. So the forward reaction goes to completion, essentially no reverse reaction. Starting to get it there? If we add in electrical cell potential, here it would be, if we start where we ended, this would be a large electrical cell potential. At equilibrium, electrical cell potential is 0. Its K is the one that's 1. Okay. And then here, when it's not thermodynamically favorable, your electrical cell potential will be negative. This is not confusing at all. I think y'all got it though. All right. So there it is, like one more time, if you need, like just one more time. So here is you a nice, now this is 6-part FRQ, so I'm going to give you like 20 minutes to do this. No, don't, avert your eyes, crisis. There we go. I'm going to pick this pen, it seems to work better. What?
Reaction X represented above spontaneous.
This is, look at the year, 2006. Okay? So you still know what it means, okay? We have about 16 more minutes. Remember, if you decide to use a Le Chatelier argument on a FRQ, you need to make a Q versus K reference. This Q will not have that because it's 11 years old, but I'm trying to help you out. About 14 minutes left. about 7 more minutes. So we have about 3 minutes. It's a really good question. Did you something? You guys should go back? Ooh. It's okay. We're still learning.
The gives free energy, because you have to find the gives free energy to solve for the equilibrium, right?
On B?
Yeah. Once you find that, you have to switch the kilojoules back to joules so you can use the constant.
You can just use a constant.
But you have to change one of them, right? Because if the gives free energy is in kilojoules and then the constant is in joules, you have to switch it, right?
What do you? The equilibrium constant doesn't have a
No,
unit.
the R constant.
Yeah.
Okay.
So you change the gives free energy to joules. But yeah, you got to be careful there. We're gonna talk about that.
Could you change the constant?
Yeah. Either way.
Why certain solids
You will. To get
Oh, I didn't even
IT, you
look at
have to
that. Yeah.
reverse that.
I just say
I literally was like, 'cause I was like,
It's like
that's like the only thing I can think of.
I didn't even look.
What they typically do is they change the Gibbs free energy to joules in the problem. I think it will come out in the wash though. We'll see. All right, your time's pretty much up, my friends.
I changed. I changed it. That's. Oh, it needs to be in joules.
You got a couple seconds left.
What was the Gibbs free energy?
Gibbs free energy is kilojoules per mole. Okay. So. And that's why when you do the Gibbs free energy formula, you have to change entropy to kilojoules. But then when you use the other equation that relates K to Gibbs free energy, because the R is joules, but everything's on your formula sheet, it'll lead you the right way.
Yeah.
You just kind of have to be, when you're doing thermodynamic stuff, you just have to be like,
Yeah.
just be careful, right?
Aw.
Okay. Hello, sweet children. So, if you recall earlier, we had said, on some of these you can do calculation, and on some of them you can sort of eyeball them based on the entropy and enthalpy values. In this situation, it said to do a calculation, so I guess you better do a calculation. So make sure you read the question. When it says justify your answer with a calculation, do the calculation and then come back behind it with written thoughts that explain why your calculation supports the answer. Got it? Calculate the value of the equilibrium constant. There's some sticky points there that I'm going to go over as I show you the key. See what effect will the increase in temperature have on the equilibrium constant? The key that I'm going to show you for this older test doesn't have a Q versus K argument, but please listen to me when I tell you to do that. Explain why the standard entropy change is greater, which that one should have been pretty straightforward. Above at what temperature does the value of the equilibrium constant? So really, at that situation, you're solving for 1, and then is it bigger or less than 1? That's kind of confusing, so we'll get into that. And then the last one, you have to combine reactions. It's like a fun little matching game. I enjoy that. I don't mean it. All right, so the first one, when we have Gibbs free energy, this formula here, when we do this, we're going to change entropy to kilojoules per mole, which they did. Okay, and then because your Gibbs free energy needs to be kilojoules per mole. 1 point is earned for the correct value, and 1 point is earned for the correct justification. And your justification here, like I said, you're going to go off the work you did and provide a written statement that's supporting that your claim. So in this situation, Gibbs free energy, since it's negative, and you could say negative, you didn't have to say less than 0, but since it's negative, then it's thermodynamically favorable. Yes.
For all of these, I'm getting answers that are one more significant figure than what they have up there. I don't see why this one wouldn't be 2.
Maybe there's something in the problem.
I can tell you, okay, I don't think so, but the deal is here, there will be one significant figure point, and it will be based off of, the student is doing an experiment. This is the data they get from a thermometer. This is the data they got when they measure the volume. The significant figure point, I mean, I agree with you, but the significant figure point will come from like a database question based on lab work, because that's really the situation they want you to be able to use significant figures. So there will be 1 point based off of that, but especially when you're doing like in the lab, blah, 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 or a measurement is made, blah, 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 that's your significant figure point. That's your Q, okay? But not the Q versus KQ. That's not funny, is it? Sorry.
I think -2, like for the power B. I don't know how.
Wait. So are you talking about A?
No, B.
Okay, on B. Calculate the value of the equilibrium constant. All right, so look here, guys. What they're doing is when you do this formula that gives free energy, and this R here, that's going to be the first R that is listed on your formula sheet. So that's like If you don't remember, it's the first one, okay? When you're doing this, that R value for that constant, that universal gas constant, is joules per mole times degrees Kelvin. So if you'll use that constant as kind of a guidepost for your units, it'll help you get there. You have to change your Gibbs free energy into joules because of that. So that's what they're doing right here. They're changing it into joules by multiplying it to 5,000. That's what their work is showing. And then they have the universal gas constant. And when you work it all out, everything cancels. And yeah, everything cancels. And they got 2, right? And then KEQ, did you forget about the natural log part? Because here's the 2.
I just left out. I just didn't use the other negatives, they didn't cancel. That's all.
Okay, so your KEQ is equal to 8. How you feeling?
Yeah.
Okay, not good? Do you want me to work it out by hand for me? Okay, first of all, they rearranged the formula before they started to kind of isolate the variable they're solving for, which is K. But you have the natural log of KEQ. So remember when you're trying to get rid of a natural log, you're going to raise both sides.
For some reason, I only have one value on the top.
You didn't switch the kilojoules.
You have to switch it to, the kilojoules and the value for Gibbs free energy to joules.
Because of R.
Because the R, the universal gas constant, has joules. And you need, your equilibrium constant should have no units, so you need everything to cancel. So if you set it up correctly, do your question, you'll be able to tell. So is that what it is? Did you leave it as
Right,
5?
okay, so the 10 to the third joules on the top is just converting to it.
Yeah, so this is really negative 5,000 joules. You could have just written it out simple as that.
So you don't have to show the, so like I changed the R, do I have to show that I did that? Or can I just write, like I can just, like I changed it to,
As long as you showed you're changing units.
Does it like matter?
but like I don't have to write out the whole calculation, like I put kilojoules instead of joules.
No.
Do what?
This is not like it like that.
Okay.
You're good.
Good.
But yeah, simple things where you're going from kilojoules to joules or milliliters to liters. You can just show like the 1, 2, 3 little bumps of your decimal place, and that's sufficient.
Does that shouldn't matter which one we change?
Did it matter for you? It shouldn't matter.
I mean, like not answer-wise, but you know, sometimes we like you get a point for changing the kilojoules to joules.
Yeah.
But you're doing that, right?
Well, I mean, like, you know
For
what I'm
this,
talking
in this situation, I don't think that's going to be applicable. Like your final answer, where it's, for example, if you're expected to have Gibbs free energy and it says kilojoules per mole and it says that, you leave it in joules. They don't typically give a point for that. Yeah.
So on the next part,
Part C,
yeah, so if I don't make like a Q versus K argument,
you're going to probably lose a point.
okay.
Look, all the people that do that better at this than me, and the people that grade it, and the people that read it, have told me that over and over and over again. I'm not just being a pain in the butt. Like, I'm serious. You have to do it.
Okay,
I've told-
'cause, like I just said like the thing about the smiling faces. Like I wrote about that.
The thing about this, because they're asking specifically about the equilibrium constant, we're no longer talking about thermodynamic favorability.
Okay.
See what I'm saying? So,
Yeah.
right. So on C, what will the effect on an increase in temperature have? So what you probably wrote based off of what you know is the enthalpy was positive. So an increase in temperature will cause the reaction to shift to the product side, right? Because it's endothermic. And so when a reaction favors the products or the shift happens for the reaction to favor more products, that will increase the value of KEQ. And then you just need to write Q is less than K. You just need to do it. This is just like A's, like there's magic words, and I told you the magic words, and then you did the things, right? Yes. All right, and now on D, why is the standard entropy change greater? Did y'all have any trouble with that?
No.
All right, God bless America. Yes.
So you don't necessarily have to explain why liquid would have lower entities because it doesn't. It just says they have lower entities.
I mean, I don't. The thing that I kept saying about, because there's a lower number of possible arrangements, I haven't really seen that too much. That's the right answer. But, I mean, if you're worried about it, that wouldn't take 10 seconds to write. So, you never, the thing is, you don't ever really know what the key is because they don't really know what the key is. They don't make it till they get there.
But
Yeah, they kind of they make the scoring guidelines specifically for apes, at least at the reading.
You know how it says 1 point is done for a correct explanation? Does that mean like any correct explanation or like when it's like that?
So what happens with that? Like if it's not in the key, what we have to do if we're reading, we have to talk to our table leader and say, is this acceptable? Okay, and then they have like a big chart of things that you can take and they add to it. I mean, it's crazy. But so not everything is on the key. Excuse me, above what temperature will the value of the equilibrium constant be greater than 1? So what do you want it to do? When it says greater than or less than 1 or greater than or less than 7, what you do is you fill in the equation with that number. And then you use your brain to say it had to be less than or greater than that. Because it's kind of hard. Like if you just filled it in with 1 and you got 330 degrees Kelvin, you're not done, right? So we already talked about, since it's endothermic, if you increase the temperature, K is going to be larger. Y'all good? So you would have to then say the temperature would have to be above 330. Do you see how you can do that in your head?
So you can just not include the natural log of K or the it's like, because my problem was like the natural log of K, or sorry, the natural log of 1 is 0, so that's what threw me off. Yeah, like in my
This formula doesn't have any natural
Oh, I
logs.
used to, I was like,
So you just
So
did 0
wait, if you
equals
use the other one, you get 0.
yeah, that's what I used the other one trying to use.
And it
Okay.
didn't work.
and then you put 0 equals to the H minus T.
So this is actually an easier way to go.
Yeah.
Because
that
when K equals 1, like that thing we said over and over again, gives free energy 0. Right? So
You would actually use that one.
the other one, I didn't think to use the other one because this one's easier. But so when you fill it in the other way, you get 0.
Yeah, well, natural log of 1,
It won't work because you have to
yeah,
rob it
like
zero.
this is 0. Yeah, and no
okay.
matter what way you do it, like this.
Okay. So you got 4 options for Gibbs free energy, so you can just switch up your options. I see what you're saying. And you know, if your answer doesn't make sense, you're looking at a temperature. Well, anyway, for the vaporization of solid iodine, and it's a your answer if it's 0 degrees Kelvin, no. We're not hitting absolute 0 in here, right? Okay. So anyway, for the vaporization of solid iodine, here is the enthalpy value, and so what you had to do, was it this one that was given to you at the beginning of the question? Yeah, and then you had that one. And notice here, look, if it's enthalpy or Gibbs free energy, if you add 2 reactions together to make this overall reaction, then you're just going to add the enthalpies. You don't have to do anything crazy. It's the multiplication and stuff that comes with the equilibrium constant. How you feeling? Speaking of, really, do I need to explain something to you? Sure. So, did you need some help with F? Like, do you just need maybe another minute to do F because you ran out of time? Okay, why don't you do F? And then when you're doing F, here is your here's your overall reaction that you're going for. And you saw for the enthalpy of the iodine reaction, that you need to start combining stuff, reversing things if you need to get the overall reaction you're looking for. So take a second to do F if you struggled with it. I'll give you until about 10:33.
You do that?
You can't do like. You can actually see.
You really have to do the rest of it to like get the vibe. I'm an epic boy.
We'll see.
I feel like I may need to work out F for you.
Yeah.
Do the things.
Why do you even need
Yeah.
Why do you even need one?
the vaporization?
Because in the top one is a solid. It's
Right.
just a gas.
So states matter.
Oh,
Yeah.
okay.
So I was already seeing how that was not working out for y'all in y'all's head. It's okay. I gotcha. No worries. I'll have it pulled up over here.
I've tried. I honestly still don't. Question.
I did it.
I know my argument I was like, it's hard. So I sat there looking at it for like 5 minutes.
So it's like a little puzzle. Okay. Alright. I haven't done the math. I'm gonna explain that.
No, I just like I can't tell from your work. I did like you have to.
I'm about to explain. I was just trying to say calm. Hello, sweet children. Alright, look. So I see that this overall reaction I'm going for, it does matter about states of matter. Okay? Then states of matter matter. Anyway, I'm going for iodine as a gas, fluorine as a gas, and 2-ICL. This 2-ICL, given that, this reaction is present, that's your big glowing sign that, hey, I need to bust out reaction X because I have to have some ICL, right? Like that's, okay. Now, if you look at ICL, you can already tell you're going to have to multiply it by 2 because you need 2 ICLs, and there's none of this. So, and you want ICL to be your product, so you don't need to reverse it. So you're just going to take that enthalpy, and this enthalpy here, this one, you're going to multiply it by 2, right? I mean, are you lost? You okay there? Okay, and so the other reaction they gave you for not paying attention, you have to pay attention because the solid goes to gas. And then if I look at this overall reaction I want you to have, I need gas on the reactant side. So I'm going to need to reverse that reaction. And when you reverse that reaction, you get this. And when you reverse the reaction here, you're going to have to flip the sign. So you end up really having what, was it 36 plus negative 62?
Yeah.
So you got what, negative 26? Yeah. That's it. On these, you just need to get your little paper and you need to start looking at what's on which side. You need to reverse stuff. What is in the final reaction? Are the coefficients such that you need to multiply by 2? You got to work backwards. And I did work backwards. I started with the end of where I was going in mind. So you're given a reaction and you have to make it. You need to start hunting for things that you can combine. Feel a little bit better? Logan, are you still processing? You can process. Go ahead with your bad self. Do you have a question?
A little bit.
So what the thing is, they're asking you, hey, what's the entropy of this? That's the question. You can tell from, I mean, it's like a little buffet. You don't have to pick stuff, but you may need a scoop of this or that, right? This doesn't help you at all. Nothing. But I need ICL on this overall reaction, so now I'm going to be using reaction X. I can tell from the products that I have 2 ICLs, but that's got only 1, and these have halves. There's no halves down here. I'm going to multiply that first one by 2, and that'll help me. So if I multiply that first one by 2, I got it knocked out. But then this overall reaction up here has gas iodine as a reactant. If I don't flip this, I'm going to end up with 2 gases on the, I'll end up with the gas on the, this side. So you have to flip it to make the solids cancel and have gas where you want it.
Okay.
Yeah, y'all are actually really good at this kind of thinking. This is like elementary school gifted, like those little word problems. Who went to dinner first? Like, I swear that's it. Do you know what I'm talking about? Yeah, this is like that. You just need to approach it like a little game. And then, like I said, these are your choices. You may not need to know that Sally went to dinner with Jim, but you might. So just use what you need. Those were fun. I miss those days. Anyway, guess what's next? Yay!
No.
Yes.
No.
So good news is this is the last big idea. Bad news is it's equilibrium. But other than IMFs, I mean, this is really heavily tested. So even if you don't like it, you need to just embrace it. And don't let these kinds of problems scare you, because there's always going to be intermixing of content in there. All right, what is equilibrium? Equilibrium is when you have a state where the rates of the forward reaction, so check it out. The rates of the forward reaction equals the rates of the reverse reaction. They're constant and equal. So this is if I'm given any data before you hit equilibrium, I'm going to be making a reaction quotient, and then I can figure out if I'm at equilibrium or not and which way it will shift. So anyway, once the rates are constant and equal, then you're good. Now this is a rate. The rate is change, right? Change in concentration over time. So rates are always slopes of lines. Did these lines have the same slope? Yes. Does it mean that I have the same amount of reactant? No. Or products? No. It's the rate is the same, not the concentration. The rate. The proportion of products and reactions are going to be in this situation. You can write an equilibrium expression. A lot of times on these questions, it's 1 point for writing the equilibrium expression. Just take that as a little Christmas present and do it. Watch your coefficients. They become your exponents. Okay, manipulating Q versus K. Here we go. K is the equilibrium constant, relative amounts at equilibrium. If you're solving for something and it doesn't say at equilibrium, you are writing a reaction quotient, and it ain't equal to K, it's equal to Q, which stands for reaction quotient. Q and K, so this is your reaction in progress. Describes the relative amounts at any point. If it says at the beginning of a reaction, the concentrations are blah, 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 blah. Like you hope for that. That's an easier kind of question. You set Q equal to the equilibrium expression and you fill stuff in. You can't make an ice table because it's not equilibrium and you don't have any values. If it just says at the beginning, blah, 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 blah. Okay. Q and K only include substances that are gases or aqueous. Y'all know it has no solids, right? Like we got that. We have, and no liquids. So if I'm given this reaction here, P4 plus 6Cl2 gives me 4 PCl3. Here's my equilibrium expression. It's only going to contain that chlorine gas. That's it. The other one's solid liquid. So, let's see. Oh, here's a good example of stuff that we already did. Here's your little matching game. I wish you will. Here's a question right here. Take about a minute and a half. This is not a multiple choice question, but these show up a lot like it's a multiple choice. We already did this. We did this like 27 minutes ago. No, it's been like an hour. So this is a review of that chart. Yeah. I'm having a fun. But this is what y'all were struggling with on that last one. It's a great opportunity to practice. That red one is is the one you're going for. Now play your little logic game. I'm already having a psychic vision of me having to work this one out. If you're trying to do this without writing on your board, you can't. Unless you're better at math than me. Good luck.
Wait, you mean
Hush your face.
the answer? Like the K3? How you do that without the writing on the board?
I have people staring at the board hoping for magic. No, get busy. I'm gonna take a picture of this because I'm gonna need it.
Hold on a minute.
Do y'all all have these reactions? I need to go to the other screen. Do you have at least the reactions written down? No? Can you take a picture? Because I really feel like I need some room to write it out and like show you my thought process. And I can't do that on this one. Everybody got a picture or written down?
Hold up.
Do you need help?
Well, my board's wiping, I can't write on it.
So go get another one. I love you so much. You have to have a mental fortitude. There's my motivational speech of the day. That's all I got, really. Alright, I'm going to write this out, and when I get finished writing it out, I'm going to go over it. Alright, here goes.
Yeah, can't do that. I get that.
What number, how do you think the application
So did you raise the one
I just went over this one now.
Yeah.
It's okay, so you have to lose it.
I got reversed.
I did raise and.
I'm not wording right.
So you normally do that.
No, I guess very opposite.
Half hour reverse, and then go over that.
Oh, but they're okay now.
Yeah, it's the
What
same.
year is that?
Kind of,
And then try-
not really.
Did you get full for like the negative 6 months?
Okay. Y'all look like you're in deep
Wait.
thought. Are y'all ready?
Back to the values real
What's
quick.
wrong with it?
Those are the K values.
Yeah.
I mean, I need to write them out anyway.
So we just gotta, I mean, we're doing the same process, but we get different numbers. What would you get? That's what he.
Yeah, we
know the same thing.
You probably put a value on it.
both got 0.39.
I mean, I don't think it's, I think it's depends on where you're from.
Yeah.
Cause like this number, did you put that inside your calculation or did you do this?
I think she just like,
I didn't get that.
So, did you,
yeah, that's right.
and did you take it to
I'm ready.
Right.
Hello. This is what I do. When they always give that target kind of final reaction like last, but I feel like if you write it first and you know, well, this is my goal, and you kind of keep it as your goal, like it'll give you something to reference to. So immediately, as I look at this first reaction, I know sometimes they'll give you more reactions than you need. If you may not need them all. I can already tell you though that I need both of these because this one doesn't have any carbon dioxide, this one doesn't have more. So you may not need them all. It's like a buffet. You have to pick what we actually need. Now, just looking at the coefficients, I'm going to have to divide this one by 2 because we talk about when we multiply a reaction, we have to raise the K to that power. It's better to think about multiplying that reaction by 1/2. You see what I'm saying? So anyway, I'm going to multiply this one by 1/2. And when I multiply it by 1/2, I'm going to have CO2 as a gas, and that state does matter. And that's going to give me just CO, and I'm going to highlight this so you can see the difference. And then 1/2 of an oxygen. So let me hit that with a highlighter so you can keep it straight. So this is what I'm working with so far. Looking at my kind of target here, my carbon dioxide's looking good. My hydrogen needs to be a reactant. I know I'm going to have to reverse this one. Also, when I'm looking at the coefficients, what do I also have to do with this one? Get them multiplied by 1/2 as well. And reverse. Make yourself some notes while you're working so you have kind of a running track record of what you need to do. So anyway, I'm going to reverse it. So I'm going to have 1/2 of an oxygen, and then that's a gas, and then H2 as a gas. Notice how I'm keeping this nice and lined up. This is just like the 3rd grade, line your stuff up. And then that's going to make 1 water. So I'm going to highlight this so I know where I'm at in my life. These are what I have, and if I start to cancel stuff out, my oxygens, like that goes away, and I'm left with carbon dioxide, hydrogen, carbon monoxide, and water. So I know I did it right. So now what I'm going to do is this first equilibrium constant, I reversed it, so I'm going to take in my calculator, put this number in, and raise it to power of 1/2. Whatever that number is, I don't know. The first one I didn't reverse. I said it when I did the second one, and I wrote it down right there. So when I put that in the calculator, I just hit the wrong button. Got the life. What do y'all, do you know the number?
4 times 10 to the -6.
Say again.
4 times 10 to the -6.
Okay, and then the second one, you're going to have to raise it to a power of 1/2, and then you have to take the inverse of it. Isn't that so much fun? I love this. So I'm going to raise this to a power of 1/2 first, and then I'm going to take that answer. So when I raise it to a power of 1/2, I get 1.3 times 10 to the -10th, and then to the 1/2 power, I get 1.1402 times 10 to the -5th, and then that number, I have to find the reciprocal of it. So 1 divided by that stuff in my calculator, and I get 8.7706 times 10 to the 4th. I'm having to kind of do this in my head because my calculator's not. How's that? Now am I done? No. When you combine reactions, you're going to multiply their equilibrium constants. So I need to take this times this, and that will give me K3. So the answer is 0.35. Yeah, do you feel a little bit better about combining reactions now?
If I had my calculator, I forgot it.
I have a calculator.
No, it's
No, it's here. Give this.
no, it's. I'm not used to using these calculators. I haven't used those since like 8th grade. So it's good.
You need a correction. Alright, so that was fun. I had a good time. Let's go back to the PowerPoint now that we finished like the first half of the first slide. I like it. It's good times. No worries. Well, at least now if you have to combine reactions, you'll feel a lot more comfortable about it on Monday, or at least I would hope so. Alright, here we go. We just did that. They got 0.35 as well. Good for us. Alright, kinetics and equilibrium. We already talked about this, but kinetics is the same as the rate. Rate laws are used to describe how reaction concentrations affect a reaction's rate. And so your rate law expressions, we did that a lot last week. Rate is equal to K times the concentration of the first reactant raised to the order. It's not kinetics. You don't use the coefficients, right? It has to be experimentally determined. Equilibrium describes a state at which the rates of the four reactions are constant and equal. If the rates are initially unequal, the faster direction depletes its reactants, right? At the same time, the slower direction accumulates its reactants until they reach equilibrium. So the graph on the right, after equilibrium has been achieved, there we go. This happens a lot, these kinds of graphs, so we do need to talk about this. They'll say, they won't show all this, right? They'll just show this left-hand side. They'll say this system is at equilibrium, and they'll have all of this not in the picture. And then they'll say, what does the rest of the picture look like? I mean, that's not how I'm going to say it, but it's basically the idea. So the graph to the right, after equilibrium has been achieved, additional hydrogen gas. So they put in more hydrogen gas. I'm trying. There. Additional hydrogen gas is added. So if I add more hydrogen gas, obviously I'm going to see a jump in hydrogen just immediately, right? Right? And this reaction is H2 plus N2 gives you ammonia. And that's not the coefficients. I mean, it's not balanced, but that's the idea. So it's just a little Haber process there. Anyway, if I add more hydrogen, what's going to happen is the rate of the forward reaction will increase, right? So what you're going to do, the concentration of hydrogen will start to deplete, but also the nitrogen will, because the nitrogenicity of the reactant. So your concentration of nitrogen will decrease in order to react with the added hydrogen. And y'all know that from Le Chatellier, right? But as these two decrease, your amount of ammonia will increase, and then there will then come to a new equilibrium. So how do you feel about that? Okay, so that's easy. You can see that this would jump and then decrease, but you have to infer that the other reactant would go down and the products will go up. You know all of that, but can you put it with a graph? Yay! Q versus K. They, on this Q versus K for them, what they have is this steppy stair thing. I like a number line, okay? So if Q is less than K, it's going to shift toward the reactants. If Q is greater than K, it's going to shift toward the products, right? Make a number line. I don't know. The bar graphs don't help me that much. What they're showing here is they're showing the amount of reactants and products. So I like it in that sense, but it's just simpler to do the number line. So equilibrium is reached when the rates of the forward reaction and the rate of the reverse are equal, which is where Q equals K. So if you're given some concentrations, it will say either at the beginning of a reaction, here's your concentrations. We did one of those the other day. Or it will say something like, at a point in the reaction, here's your concentrations. Unless it says at equilibrium, you're doing a Q value, not a K value. And the K will be given to you in the problem. Ka is equal to blah, 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 blah. Okay? Enables us to determine if a chemical system has achieved equilibrium or need to move towards the reactants and products to reach. So if K is less than Q, it will proceed in the forward direction, right? If we have a number line, K, there's Q. It's really that simple, you guys. again, for the 5th time today, if you're using an FRQ and it talks about equilibrium and it's a Chatelier kind of thing, you gotta talk about Q versus K. If Q is greater than K, then it's gonna shift toward the reaction side. Okay? Q is equal to K, then you're at equilibrium. So, anyway, good times. Calculating K, yay! Alright, equilibrium constants can be determined using experimental concentrations of reactants and products at equilibrium. To determine the equilibrium constant, you're going to write the equilibrium expression, determine equilibrium molar concentrations. When you're solving for the equilibrium constant and you're making an ice table, you have to use the E line because you're making an equilibrium constant. You want the E stands for equilibrium. So anyway, determine the molar concentrations, substitute the quantities in and solve. Here's an example. I wish you well. You will need a calculator. Do you see how it says at equilibrium? That's how you know it's equal to K. If it doesn't say that, then it's not. Welcome. This is what we're doing. It's okay, they were doing APUS. We're 3 hours in, y'all.
I totally just skipped paper.
Huh?
I totally just skipped paper for you. Like all of it.
It's totally fine.
Like every single one.
Even the after school.
I like your priorities.
It's harder, so.
It seems so. Y'all got it? No. Then be quiet. I love you. Hey guys, we're just solving for K. We don't need necessarily any other information, so we don't need an ice table at this point, right? Here it comes in, knocks it out, not one on it. I do hope, as I get ready to go, I hope y'all notice that this is in a 2-liter vessel. And You ready? I'm ready. All right, so if this was the FRQ, the equilibrium expression itself would be 1 point. Okay, so there's your 1 point. Now, notice here that it gave you moles. Molarity is what we need for the equilibrium expression. Molarity is moles divided by liters. So you have to take those values they gave you and divide them by 2. So if you divide them all by 2, that's what you get. When you fill the numbers in, the coefficients were all 1s. We don't need any exponents here. We fill them in, this is what we get. That should have been pretty quick. Love you. If you got slowed down, was there anything that, hampered your ability to do this? Is there anything I can explain? So when you would make an ice table would be if they were asking something about initial concentrations or there's something missing, but they're not asking that. All right, here's another one. Calculating K equilibrium constants can also be determined from both initial, this is the next thing, from both initial and equilibrium concentrations using an ice table. So you're going to write the equilibrium expression always, determine the molar concentrations, determine the equilibrium concentrations using an ice table, and substitute quantities in there and solve. So here's your next question. Initially, that is your big glowing sign, that is the I in the ice table. Initial change in equilibrium. Initially, a mixture has these molarities of gases that's allowed to reach equilibrium. No N2 was present initially. Equilibrium NO had a concentration of 0.062 molar. Determine the value of K, and here's your reaction. This one should take you a little bit longer. See, you're good at equilibrium. Everything's fine. You're going to get acids and bases here in a minute. Yay! I'm going to give you about 5 minutes to do this. So till maybe like 11:07, 11:08, okay? I feel like you have about a minute left. I don't remember what I told you, but I feel like I said it like 11:07 or 11:08. How's your ice table memory going? I'll make one if I need to. I welcome thee. We are doing the equilibriums. And this has been streaming all morning, so y'all can catch that if you want to on my channel. I feel like such a hipster when I say that, but I don't mean it. I'm just trying to keep people from failing the AP exam. Okay. Hello. So your ice table is going to allow you to sort of sort out the information and keep it organized. So they gave you some initial molarities, and then they gave you at equilibrium the NO. So what you can do here is you could go ahead and fill in the one that you do know, and then you'll be able to solve for X. This X is the same as this X, which is the same as this X. They're all the same X's. So once you can solve for this X, you know the final, or excuse me, equilibrium concentrations for the other one. Do I need to do this? Yes? Okay.
I didn't see the concentration of.
Okay. So listen, you would not be able to do this if you weren't given at least one equilibrium concentration. You would not know what X was equal to. You wouldn't know, that change there. And so when you solve for X, you'll find that, 2X is 0.038, and so X is 0.019. And so here are your equilibrium concentrations of the different reactants and products. Then you're going to put those numbers into the equilibrium expression and make sure you're minding the coefficients there. Yes, ma'am?
Did it say that there was no nitrogen gas? Or is that something?
It said in the question initially there was no nitrogen gas. It said that. Yep, in a sentence. Again, do I need to do this? Good? You just doing it? Okay. So that's K is equal to 6.5 times 10 to the second. So K is large, greater than 1. So at equilibrium, the concentration of the, at equilibrium, the products are favored. Look at me in the face. Look. Are you looking at me? Here's your equilibrium concentrations. If you only look at this data from this experiment, does it experimentally show you that K is large and positive? Or K is larger than 1? Does it? No. That is why you need to do the Q thing, the reaction quotient. You can't look at concentrations and tell anything. You can't just eyeball it. You need to do the math. Okay? So here, because of what you started with, because of the values that were initially present, if we were to solve for Q, then, we would know that it needed to go probably toward the reactant side. I mean, it's pretty obvious. But you never really know. You need to do the math. All right, calculating equilibrium constants or concentrations with K. So this is kind of going backwards, right? What if you're given K and you're asked to solve for the bottom line of the ice table? So you're going to write you always start with the equilibrium expression. Set up an ice table. Put the stuff in that you have. Solve for X. So here's a bunch of instructions that tell you to do the same thing. You're just filling in what you know and going from there. So here's your example. Here's your question. Given the following reaction at 1373 degrees Kelvin, why did they give you the temperature? Well, first of all, it doesn't really matter in this situation, but do remember, not for the K in kinetics, right? Not that K. Not rate is equal to K times the concentrations raised to their order. Not that K, but kinetic equilibrium K, only temperature changes K. Only temperature changes K. Okay, so if we change the temperature, whatever equilibrium constant we get is changed. I just wanted to bring that up. So here's your K value. Here's what you have. Read it very carefully. Make that table first. Write the equilibrium expression first, and then very carefully fill in what you know, and then just treat it like a little fun game. Whee! I'm going to give y'all 5 minutes on this one, too. If y'all will close that back door, I will hit that button again. Thank you. The air keeps having to have like gentle reminders that it should come. Gentle reminders. This is KP. Make sure you use in parentheses. Yay! When you write your equilibrium expression, don't lose that easy point because you wrote brackets instead of a parentheses.
So there's no to the initial.
Yeah, if they don't tell you this, then. I'm going to work this one out from the beginning because I feel like when I say things over and over again, that helps you, even though you're like a little sad that I keep saying the same things. Sorry. I want to be the internal dialogue in your mind. You guys got it, or at least got the numbers, so I can move on to the other screen? Okay, cool. The solution only has the answers, it doesn't have the work, so I'm worried that if you need to see where you went wrong, you won't be able to. So let's do it. Whee! Let's make that go away. So if you're still working, then finish it up, but I'm going to go ahead and write the balance equation, which is real simple. Cl2 gives you 2 Cls. These are gases, both of them. So the first step, when you're asked to do any kind of equilibrium problem, you need to write the equilibrium expression. So the equilibrium expression in this situation, when you start to read the question, it says ATMs. So that means it's Kp. So if you can't remember all that, it's on your formula sheet. So Kp is going to be equal to product over reaction. So it's going to be C, and it's really like PCl in like a little number, but let me show you. I don't know if y'all remember this. Okay. You know what I'm talking about. And that's going to be squared over the P pressure of Cl2. And that has no coefficient. So that's my equilibrium expression. Now I'm going to go ahead and come over here. I'm going to do my ice table. I'm going to carefully read this to determine to fill in. So it gives me the temperature. That doesn't matter because the temperature doesn't change. But if it did, K would change. So the partial pressure initially of chlorine gas is 0.500 ATMs. And the initial pressure of this one is 0. And it gives you the K, right? So, but it doesn't tell me anything at equilibrium. None of that's there. Okay? So this is minus X. This is plus X. And so I'm going to have... Oh, yeah. Thank you, guys. Good job. I give it. So this is negative X, and this is plus 2X. So what I do know now is I can fill these into my equilibrium expression. So Kp is equal to 2X squared over negative X. Yeah, it told, I was like, negative X, I was certainly like, where is this going? I'm so glad you said that. You're so smart. I'm proud of you. This is one of the situations where the K value is 1 times 10 to the negative 4, so we can negate it, yes.
Also, isn't the top just X and it's squared because of, like, it's not 2X outside, right?
What?
It's just like X and squared on that side?
Oh, no, it is 2X squared.
It's 2X.
Oh, yeah, all day long. I'm sure about that. Anyway, so I'm sorry about that. When you have this negative X, remember, like, if you don't negate this, which you can ignore it, and you always can ignore it on the AP exam, you want to break out the quadratic formula. So I don't play that game. I'm not doing that. So anyway, we're going to put 0.500 into here. That's the pressure. Thank you for keeping me straight. God knows I need it. So anyway, if you're not good at this, write out 2X times 2X so you don't mess up. I'm really talking to myself right now, but that gives me 4X squared over 0.500. Now, what do I do now? Kp is equal to this. Well, Kp, if you recall, was equal to 1.13 times 10 to the negative 4th. So that's equal to 4X squared over 0.500. And I isolate my X here by multiplying both sides by 0.500. And if I take and multiply 0.5 times 1.13 times 10 to the negative 4th, I get a number, but I need my calculator to tell me, 5.65 times 10 to the negative 5th equals 4X squared. I need to divide by 4. Divide that by 4. And I get 1.4. Sorry. Times 10 to the negative fifth equals x squared. So I'm going to take the square root of both sides and square root of the answer. And I get x is equal to 3.76 times 10 to the negative third. Now, what we were solving for it, like we just did all that work. And when you solve for x, you'd be like, yay, I found x. And you're going to feel like you're in math class. But no, you're not in math class. You're in chemistry class. So the question is actually asking you to determine the equilibrium partial pressure. The question is actually asking you to determine the equilibrium partial pressure. So what we're going to do is we're going to take x and we're going to fill it in here and fill it in here. And when you do that, we're going to take 0.5, and it probably won't change the value very much, but we didn't mean to do that. 0.5 minus the answer. So you end up getting actually 4.96. So it was statistically a little bit significant. Sometimes if it's small enough, like it won't even change it because of sig figs. My calculator is not. Okay, it's 0.496. There we go. All right, so there's that one, and then 2 times that value. You get 7.5252 times 10 to the negative third. How do you feel? I think it's very tempting when you do a lot of work like that and you get X to feel like you have a sense of completion in your life. Do not be led astray. Chemistry is just like that extra step that makes you sad. So let's go back to the PowerPoint now that we've had that fun little party. Everybody's like, I'm not having fun. I don't know who you're talking about. The answer's right here on the slide, but we should have gotten the same thing, hopefully. You love equilibrium, do you really? Well, there's the answers they got, which is what we had, right?
It's not bad until it's like acid-base stuff.
Yeah, it's not bad to get to acid-base stuff. I agree, let's get there. Does anybody need my help? Good. Next, magnitude of K. I feel like we've already talked about this a lot. If K is small, you would have mostly reactants at equilibrium. If it's intermediate size, and I don't like how they have it. This is very subjective. But large, you have mostly products. So I feel like we have talked about that. If you can't remember this, just remember if the K is little to the left, reactants are favored. And then the opposite is true if K is large. Okay, yay! Here's a perfect question that relates to that. Good luck counting circles. I wish you will. This should only take you like 1 minute, like 1 minute. I actually took this from an old test of yours. Mm-hmm. Yeah, I had to go back and edit Big Idea 6 because I didn't have any questions, so I added these in, most of them. And it was like the one that needed the most questions. You guys got it? All right, so if I'm looking up here, I'm seeing that I have mostly products, yes? And then I just have a few reactants. So K is large and products are favored. I mean, are you? But you know what? If you didn't know what you were doing, it could be tough. Okay, here's Le Chatelier. Do we really need to talk about this? I'll talk about it a little bit. All right, so if you add a reactant, it's going to shift towards the product because Q is less than K. I'm going to say that over and over again every time. I don't even care. Adding a product, if I add a product, it's going to shift towards reactant because Q is greater than K. What happens?
Where it says increase to temperature, the right shifts towards the product.
You think it's wrong? Well, can I get there and then we'll talk about it? Thanks. I didn't make this slide. I went over and added questions. But somebody really smart did. They had like a PhD. So we'll get to it. I'm serious. They said it.
Yeah,
Oh, it says it twice.
shift towards products.
Look, let me take it one at a time. I'm so sleepy. Y'all need to calm down. Removing a reactant is going to shift back towards reactants because Q is greater than K. Removing a product, shift towards the product because Q is less than K. Increasing the pressure, it's going to move towards the less gas molecules. So find the side that has the less gas molecules and make a number line. That'd be so much. If you decrease the pressure, it's going to shift away from the side that has the most gas to decrease the pressure. Adding an inert gas, they will pull that. They'll be like, well, what happened to equilibrium? You got like this thing, you're making water, you got hydrogen oxide making water. And they're like, what if you add in some neon? Nothing happens. They pull that sometimes. And if y'all want this PowerPoint, I can send y'all the link. I got you. Okay. Anyway, increasing the temperature. If it's endothermic, it's gonna shift toward the products. Take the time to write down the word heat. But you do that, and I'm happy for you. If it's exothermic, it shifts towards the products. If you decrease it, shift towards what is? Oh, okay. So one of these is supposed to be reactants. If you increase the temperature, if it's endothermic, it will shift towards the product. If it's an exothermic, it will shift towards the reactants. Yeah? Okay, so we should fix that, but I'll do it later. Which, I mean, I probably won't do it. Just if I'm being honest. Yay! And this is also from a test. This is one of your test questions. So these are 3 multiple choice questions, so take until 11:30. We're going to take a break here in a minute after we finish this little segment. When we get to, like, right before we get to acid-base stuff, we'll like, I need to eat first. Thank you. So you guys got it? Did you find this to be pretty simple? All right, good. So if you add more X2, because it's a gas, H2 is going to decrease because it's going to be used up. And we saw that graphically on that graph that had the concentrations in. Do you remember? Okay, good for you. Increasing the pressure by decreasing the volume, it's going to cause the reactants to decrease because it has more moles of gas on that side. There's 3 moles of gas versus 2. And then increasing the temperature will cause H2 and X2 to increase because it's exothermic. All right, Le Chatelier. Le Chatelier is everybody's like go-to. Like I already told you, it does not help you to say his name. It doesn't matter. Like that is not going to work. So you need to say what's going to happen, and then you say Q versus K. Does not help you to say somebody's name. Systems at equilibrium can be examined using the Chatelier's principle. Blah 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 blah. So I think you got this. Here is a question. The Haber process, which they use a lot, that's making ammonia. This is why we have increased our agricultural production, but that's apes, and I wish I was there. The Haber process is the industrial process that is used to manufacture ammonia. It relies on the establishment of an equilibrium according to this. So which of the following will maximize the amount of ammonia formed in the equilibrium mixture? So this one's a little bit harder than the one she just did.
Did you say this was a test question?
I don't think this is a test question from.
I've seen this question.
It's on the AP Chemistry question of the day. I don't know if you said. Okay, never mind.
I've seen this
I
question.
get those emails, but I never open.
I swear this is on a test.
Yeah.
I remember this question.
I don't know.
I remember this.
Maybe it is from your test then.
Like,
I remember adding it in, so it probably is from your test.
I got here at like 10:20.
Thanks, Nat.
Meg, you like an hour.
I'm glad you're focused. That's good. Do you guys got the answer?
No.
Well, then be quiet. I'm so nice. I'm on tape, but I don't care. Not sorry.
number two that was shifted. Then like, what would you pick? I mean, I don't
Hang on. There's only one that works, man.
I know. I just said like, what if? What if? Like, is that like impossible?
That means that the question will be thrown out of the AP exam because they made a mistake.
Okay. You give me that look.
No. Well, you know how sometimes on those AP exams, it's like number 48 was not scored.
Yeah.
That's what happens.
I was tired of thinking
All right, sweet children. The answer to this one is the easiest answer, but we do need to talk about some of the ones that were not easy. So that's it. Now look, here's the deal. The equilibrium constant is actually going down as I'm increasing the temperature. So that means that if I'm adding, I don't know where my pen went. It ran off probably. Here we go. So if I increase the temperature and then the equilibrium constant goes down, that tells me that reactants are becoming more favored with increased temperature. So that means that this thing is exothermic, right? So if I add heat, it's going to go back to the reactant side. You need to be able to infer that. Love you. How you feeling? Was that one all right? Cool. I feel like we just did this.
This is cute.
Okay, I did this a minute ago because I wanted to, and here it is again. Do you got it? Do you know that if there's a Le Chatelier type question, you don't say that, you say keep. Did I make my point? Okay, good for you. Acid base. I'm gonna say it's lunchtime. We're gonna come back in 45 minutes, which would be 12:20. All right, we have the food and we have break. It's gonna be great.
45 minutes.
Do you not want a 45?
No, I mean like I'm about to leave.
If you want to leave, I'm not your. I mean, this is not a school day, so if you
Okay. Peace out.
kept going anyway, so there.
Acid base particulate.
I think it's working. All right, guys, it's unmuted. Here we go. You ready? Hope so. Find a happy place. If your happy place isn't in this room, I apologize. All right. Acid. Yes, this is time to go. Acid-based particulates. We did this a little bit after school the other day, but I wouldn't really put it past the AP exam to have particulate modeling or drawn circles of acids and bases. Because on the free response, they've done it with ions and water. They've done it with different situations with ion-dipole interactions. You have to draw Lewis structures and stuff. Oh, and it has like gas particles getting heated and draw the vector arrows. So they're moving towards getting you to draw particulates, but that hasn't been an acid-base question. So like I really feel like that could be a thing. Maybe, maybe not. But if not, you still have to understand what's going on. So if you look at this strong acid here, hit the lights. I think that might help in here. Do the light, lady. Thank you. So if this is a strong acid, this is HA. So this could be something like hydrochloric acid. And then here's your water. What is this weird little growth? Those are the lone pairs on the water, okay? What's going to end up happening? This is your chlorine with its lone pair, like that's what that is. And then you have your hydronium ion. So you can see here that you have a lot of the conjugate base present in solution after the acid dissociates, or deprotonates, I should say. And then you have your H3Os. So when we write, or if you look at your formula sheet, the H3Os are again just abbreviated as H+, okay? They're, the H+ and H3O are the same thing, but when we talk about acids, we're really talking about hydronium ions instead of hydrogen ions, but it's written as H+ for shortness. I would recommend that you always go with H+, don't write H3O+, okay? You just have your HA breaks down into H+ and A-. Then you don't have to worry about this hydrogen here and that that water here and that H3O. It's just easier that way. I played around with it last year, and I figured out that was the best thing to do. Now this weak acid, we're looking at the particulates. Here you can see it's protonated, it has a proton, and then in solution, most of the acid particles, this one, they mostly still are complete molecules, but then here, this one's deprotonated. So less H3Os are going to be present, only 1, 2, because the acids stay together. What ends up happening here is we had talked about the intermolecular forces happening with acids bases last time, and the strength of acids and bases, and how the area of electron density gets pulled. In a strong acid, the area of electron density gets pulled away from the hydrogen, and then the oxygen can actually remove that hydrogen and make hydronium. We spent a long time on that last time. So if you need to look back at that, it's on last week's recording. So if we keep going, hopefully, there we go. Let me make sure. When you're finding the pH, I know I've said this, but I'm going to say it again. If you're finding the pH of a strong acid, that is the only time that you can fill in the hydrogen ion concentration into the pH formula. If it is a weak acid, you must make an ice table. There's no getting around it. Because the hydrogen ion concentration won't be equal to the concentration of the substance. So anyway, let's go ahead and look if we have a pH of a weak or strong acid on a particulate level. What does this look like? And so this is a particulate picture of a strong acid whose concentration is 0.001 molar. There's 100% ionization. So here's my original acid. If you look, not even in this present, I just have a bunch of hydroniums, right? It's completely deprotonated. Okay. You wouldn't say, it's better to say deprotonated than ionized. Like, what you're losing that proton, you're losing that hydrogen plus, okay? That's what's happening. Now here, if you look, here's my acid molecule, and there's lots of those that haven't been deprotonated yet. And I'm forming, in relative terms, I'm forming per molecule of acid way fewer hydroniums. So this is a particulate picture of a weak acid whose acid concentration is 1 molar. So notice the concentration is much higher. So 1, 2, 3, 4, so 10,000 times as strong, right? And its Ka is over here. The Ka of the strong acid would be very large. 10 to the 10th, 10 to the 30th. It doesn't matter. It's completely products are favored. Here, the Ka is 10 to the negative 6. So here's the deal. For these two substances, if I have equal volumes and if I want to have equal pHs, the volumes wouldn't really matter because the pH is going to be not really relative to volume. But for them to have the same pHs, I'm going to have the same number. Like if I sit here and count these, if there's 47 hydronium ions here, then there's 47 over here. To get 47, like I'm going to have a way higher concentration because only a small proportion of those acid molecules get deprotonated. How do you feel?
I have a question.
Yes.
Do strong acids even have Ks?
Strong acids typically don't have like a Ka listed because here's the thing: you're not going to do. It would be a situation where you wouldn't really have a reverse reaction, so you wouldn't have an equilibrium constant because the reverse reaction doesn't really exist. Virtually all products at equilibrium. So yeah, you're not. If you look it up, like if you Google the Ka of sulfuric acid, like you can find it, but it's not going to be given to you in this situation. So if you have a strong acid, you're not going to make an ice table. At equilibrium, it's virtually all products. All right, so titrations. These little curves, like they really look tricky. Like, what is this even showing me? What you have to do here is you have to take one line at a time, which I'm going to do. Okay, I find that to be overwhelming. Let's just start here with titration of. This is a weak organic acid. Let's see, whatever. A weak organic. I think that might be acetic acid. Oh no, it has an extra carb. I don't know. A weak organic acid. Some kind of what are the names of? It'll come to me. There's a special group of them. I don't remember. I'm tired.
Polyprotic.
What was it?
Carboxylate?
Yeah, carboxylic acid. That's it. Thanks. Good job. So this is a carboxylic acid, and there you go. So if I'm titrating a weak acid, notice my initial pH is going to be between 3 and 4. Okay. If I was titrating a strong acid, unless the molarity was just stupid small, my initial pH would be somewhere down here. So that's the first thing to look at. Also, my equivalence value is going to be at a pH of 8.8. Remember the conjugate base, which would be all of this minus that H, is going to be a strong base because I have a weak acid. Weak acids have strong conjugate bases, recall. All right, so here's the deal. I'm going to take these one line at a time. So if I'm titrating a strong acid, I'm just looking at this one line, okay? Now, if I look at this one line, my initial pH is about 1 or maybe a little bit less than 1. And so my curve is going to be starting at a lower pH. And then the equivalence point for here, it's kind of hard to tell with all these lines. But it should be, I know it's at 7. Like the strong acid, strong base equivalence point 7. No matter the concentration, is 7, okay? Now, if I have a weak acid, notice my initial pH is much higher. And then if I draw just this line, my equivalence pH is, maybe closer to 9. Just for that same reason. So when you see a graph like this, don't let it freak you out. It's just what they've done is they've shown you the relative shapes of titration curves based on the acid strength. Okay, that's all that is. Does that make it less scary? Because that looks crazy. I don't like that game. All right, very, 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 very important. If I'm starting with 0.1 molar acid, this could be hydrochloric acid. This one right here could be acetic acid. This could be some really weak organic acid. It does not matter. At equivalence, I'm gonna have the same volume of base to neutralize it. If you have a weak acid, let me go back and show you because I want you to understand. If I have a weak acid, do you see all these weak acid particles? That hydrogen, when I introduce a strong base, they will all become deprotonated by that strong base. So moles of acid equals moles of base, no matter the acid strength, if I'm using a strong base. And you're not going to be asked to use weak and weak. It'll either be strong, 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 weak. Okay? So if my molarity here, went the wrong way. Like I said, if I have 0.1 molar hydrochloric acid or 0.1 molar acetic acid, they still need the equal moles of base to neutralize them. Okay? They will still have the same equivalence point volume. this titration curve shape will be different. But even if I have an acid molecule that's not deprotonated, like if my acid is still together, oh, I'm sorry, don't look. Avert your eyes, it's a surprise. Am I going the wrong way? Lord, I clicked about 5 slides, my bad. So if this is my, you know, that's my anion, whatever it is, and here's my hydrogen. If I have, I'm serious right now. I'm just trying to draw y'all a picture. I'm just trying to help you out. There. If I try one more time, I wonder if it'll work. Probably not. I'm just going to use the same color. No. I'm just using the same color. If this is my there, the hydrogen's colored in. All better. If this is my acid, and it's a weak acid, and every single one of these is in the solution, and you know I have 1 million, and only one's deprotonated. The strong base will come through, and it will deprotonate every single one, even if they're still protonated, if they're together as a molecule. That is a really common misconception. Do you remember that? Here's a picture that shows it. Right? Moles of acid equals moles of base at equivalence point, no matter the strength of the acid. And if it was a weak base getting titrated with a strong acid, same idea. But the titration curves would go down like that.
It's just saying H plus and OH equals.
Yeah, moles of acid equals moles of base. H plus OH gives you water, right? And you're right, so moles of those have to equal. You gotta be careful though, because some of the weak bases, for example, have hydroxide. I mean, they'll make it in solution, but that gets a little shaky. Anyway, when you're titrating a polyprotic acid, which poly means many, protic, I'm talking about the proton, I'm talking about the hydrogen. In this case, the polyprotic acid, let's say like sulfuric acid, okay? Sulfuric acid is H2SO4. So, sulfuric acid, though, is a strong acid, so its first equivalence point would be around 7. So just know that. But what you can do, you need to look. There's one equivalence point and there's one equivalence point. These straight up and down lines where moles of acid equals moles of base, that's what you need to look at to see how many protons. So if this kept going and it did it again, that would be H3. That could be like phosphoric acid, you see. So let's just pretend that I was doing phosphoric acid. Right here at the beginning, I would have H3PO4. At equivalence point, I would have just H2PO4 left. So right here, I would start with H2PO4 1 minus. Okay, and then after I reach equivalence, at this point on, I would have HPO4 2 minus. This charge is becoming more negative because each hydrogen ion, well, each proton has a 1 plus charge. Recall? Now, listen, if you look at each additional, I could probably make this better, but each additional acid that's formed after I deprotonate the original acid, so H3PO4 is going to have a steeper kind of initial, I guess, curve, that's the word I want to use. So a stronger acid is going to have kind of a steeper curve, and then the weaker acids will be kind of a shallower curve. So each additional deprotonation, like the H2PO4 is a weaker acid, it will have a more sloped curve, and then the next one, like, will have an even shallower curve. See, as you get as you get weaker in the acids, the curve becomes kind of more shallow. So that's something to think about too. So Ka1 is higher. The equilibrium constant for this one is higher than this one, which is higher than that one. It's another way to say it. Good times. So those are some things to think about. This is definitely a strong acid, strong base. You can tell because the pH is 7. Here, this is the titration of a base with an acid. And so, is it a strong base? No, because the initial pH is only like 11. If it's a strong base, it might be closer to 13. And so, that's your buffer region. And then, they're using methyl red. Really, any indicator that's along this very rapid decrease or increase in pH will be an appropriate indicator. But you really want the pKa of the indicator to equal the pH of equivalence. Do you remember that little factoid? Hope you do. That's probably in here, but
Wait, can you say the thing about the Ka getting?
yeah. So this first acid is the strongest one. This one's weaker and this one's weaker. So if we think about acid strength in relation to equilibrium constants, larger equilibrium constants mean that more of the products will be favored, so it will be more likely to get deprotonated. So the Ka of this one might be, I don't know, phosphoric acid is not a strong acid, but it might be, I'm guessing, I have no idea, 10 to the 4th. This one's maybe like 10 to the 8. This is maybe like 10 to the 12th or something. Okay? Does that help you out? All right, moving on. Yay! FRQs. You don't want to do it, I'm sorry, because you're going to have to do it on Monday. So, this one has 4 parts. This is probably, I'm going to give you about 15 minutes. It's not a complete FRQ, but it's most of the parts of it, I believe. I could be wrong, but I'm going to give you 15 minutes, so I'm going to give you until 12:55. When you're doing titration math, it's stoichiometry. You may find that a BCA table is more helpful, or just straight up acid equals base moles, whatever you want to do. So your choice. Be careful with your coefficients there, especially if your base creates 2 hydroxide ions, which it does not in this situation. still have 13 minutes, right? So this is a FRQ, so you can use a calculator. You probably should use a calculator. You still have 10 minutes. Your friend that's helping you won't be helping you on Monday. Try to do yourself. I will go over it. Have you had enough time? No. I mean, it's not, time's not up anyway, but. If you get to D and you're like, I don't know what to do with my life, look at that formula sheet and maybe like magic fairies in your head will remind you what's going on. I saw some light bulbs went off when they looked at the formula sheet. There's a special formula for that situation when you're buffering. Buffering just sucks. Sucks with acid bases. It sucks when you're waiting for a song to start. Buffering is not, nobody likes buffering. But D is obviously in that buffer region, and there's a special equation for that. Do you remember it? I do. Alright, your time's almost up. Do the best you can.
Is this the whole number 3?
I think this one had another part or two. Yeah. That's why I didn't give you the whole 22 minutes or whatever. We have a little over a minute. as they're going to do. So let's talk about it. Whee! Okay, so if you're freaking out about on Monday, oh, I don't want to do acid-base FRQs, you just did one. Did you die?
A little bit inside.
A little bit inside, fair enough. There was the pH graph. I'll get you to do this graph in a minute. I couldn't put both of them up on the screen at the same time. And so maybe as we come back to this, what we're about to talk about might help you. Now, this is what I was talking about. If it's up to me, which I'm not taking the AP exam, I'm not going to write hydronium. I'm just going to go hydrogen. It's a lot easier, right? You don't have, if you do go H3O, then you need to make sure you have the H2O and your equation, balances. Don't do it. Don't do the water. Don't do the H3O. Just go H+. So that's 1 point for the net ionic equation. Are you okay with that? Good. So listen, at first, if you're like, I have no idea how to do this, there's always write the equilibrium expression, write the net ionic. Be careful on those because you can still screw them up. But I'm not massively in love with how they work this out. You may want me to do it my own little way.
Well, I get robbed of my point for not showing the moles of HCl at once. I do like the MD way, and I don't show the one side.
I don't know. We had this discussion. I don't know the answer to that. The way they're just setting up proportions, which is fine. If you want to do dimensional analysis, which is probably what you did, what you should have done in this situation is converted that to liters. So you would have had, if you had done it the way that I had showed you, for months at a time, you would have taken. I can't make a circle. There we go. 0.02995 liters of HCl, and then over 1, and then molarity is 1.25 moles over 1 liter. That's that, y'all. That's all that is. They did a proportion, whatever. Do however you want. On these two-step kind of questions, it's really common to get a point for going to moles. So go to moles. You got it. And then what they did was they took that answer and they. What is this? What in the world? They're just taking it and they're dividing it by 0.045 liters because moles divided by liters is concentration. You divide it by the total concentration. That's what that is. That looks way too complicated. Don't freak out. That's just a proportion. But that's what they did. So you should have gotten 0.832 molar. You got that?
So why is it just 45 milliliters?
They did this. That's how they're divided by 1,000. We would have never.
You wouldn't add to the total.
It's asking for the stock solution. It's not asking for right. Okay, so that's not bad. And I told you accidentally a minute ago. I was like, remember, you want the pKa of your indicator to equal the pH at equivalence. That's just something. We can go through the math of that, but why don't you just remember that? How about that? So you should have picked Thymol Blue, right? Has the closest. That. Even if you feel uncomfortable with the math, there's stuff you can pick through and get. And then this last one, anytime you're in that buffering region, and let me tell you what I'm talking about, right? This area, if you're from here to here, then you use the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch is the one on the formula sheet that is pH is equal to pKa plus the log of your conjugate base over your acid. And if we were titrating a base and it went down like that, that would be POH is equal to pKb plus log of the conjugate acid over the base. I don't know if they'll do that, but just be mindful. I don't believe it's written like that on the formula sheet. It's not. So, if you're dealing with that, then yes.
Wait, so when do you use that equation?
If you are in the buffering region, which is this first area before you start to approach equivalence, that's when you use the Henderson-Hasselbalch. Let me tell you what's especially helpful here. When you're at half equivalence, pH is equal to pKa. You learned that, you memorized it, but this is mathematically why that's true. If I'm at half equivalence, the concentration here is equal to the concentration here. And so when I divide, I'm going to get 1, and the log of 1 equals 0. And so pH is equal to pKa for that reason. So pH is equal to the negative log of the Ka. They gave you the Ka that they gave you is right here. Do y'all remember P means negative log of? Yeah, I know I said that a lot during the semester. So can I help you with anything? log of the strength of the acid, or the equilibrium constant. So if you recall, you guys, pKa, right? The stronger the acid, the larger the Ka, but actually the smaller the pKa is. Remember?
So that means that the hydrogen concentration equals the Ka. Like if you do like the thing now, like the expression, because they'll cancel the. Wow.
Okay,
So how did you get 2.0? Or like,
it tells you that's my equivalence pH.
so equals
No. Alright, so the equivalence in this situation, the pH is 2.54. You still good?
Yeah.
Cool. Now, when you're choosing an indicator, remember the indicator, its endpoint is where it changes color for the indicator. Equivalence is where moles equals moles. So that's not the same words, by the way, and it's not always the same value. What I'm saying though is mathematically, you don't need to know all the math. I mean, to be honest with you, the pKa of your indicator needs to be equal to the pH at equivalence, because you want the color to change where the pH is rapidly increasing. Anything else I can do for you there? This formula is only in the buffering zone. Only in the buffering zone.
For your indicator, you want it to be equal to your pH.
At equivalence. You want your pH of the indicator to be equal to equivalence, not anything else. Because that's going to tell you where your color is going to change. We did some math for that. It was kind of obnoxious. We could do it again if you want to, but I don't think that's necessary. All right, I want you to go back and take about 2 or 3 minutes and draw this graph for me. Like draw your pH curve. So take until 105.
Oh, this is the rest of that.
I don't see the initial pH. It says it's on it.
It's along the axis.
Oh, I see it now. I see it now. Okay. Sorry, I only saw this dot. I didn't see any other dots. Thank y'all. You have data that you just solved for in A through D. So
Yeah, it also told us like the volume that it gave us, but it was in the
I mean, you can just
data
use
set.
the equivalent.
do you need to go back to the question real quick?
Yeah.
There you go. Take a picture of the data if you need it, you guys.
It's only there. It's almost there.
I'll keep it here and then go back to the graph for you if you probably need this more than the graph. Do you have this stuff on the graph for the initial pH and the equivalence or no? You got this?
Oh, that was it. Okay. Alright.
I'm going to switch it in about 10 seconds. Alright, there you go. So you got about a minute. right, time's up. All right, let's take a look at it. I'll try to remind you some important things. Okay, they ask you to mark the half equivalence point on the curve with an X. Like, that isn't, like, if you circled it or maybe put a box around it, the people that grade the AP Chem exam, they're real detail oriented, and they're kind of like, well, they didn't follow the directions, and it will be in a punitive way, and I'm sorry. They're like, it was in the directions, you should be able to read. Like, they say stuff like that. Okay, let me just be honest with you. So it says to mark with X, mark with X. Now, they have this dot right here at, that was already marked for you, right? So at half equivalence, you should not just be like, oh, here's a line, I just feel like putting a line here. Half equivalence is half the volume, so that X of yours needs to be at 15, not 14, not 16, 15, okay? So if the line's here and you put if the line's here and you put the X here, no. And your graph table will be labeled in your book, okay? So that one shouldn't have been too much. Now this was 3 points, yes.
So half equivalence is always half of the volume of the
Yes.
equivalent point?
Half equivalence is where pH equals pKa, but it's also half the volume needed to reach equivalence.
Okay.
Right, so, even if you weren't able to do the math, like if you found that struggle to be real, here they gave you this dot, it's at 30, right? And so if they gave you the dot at 30, then you should have been able to like eyeball it, connect the dots, and then put your X at 15. So there's an easy free work for you. Even if you get in there and you're like, I don't know how to do this, I'm gonna fail a life. There's easy points if you just don't freak out. A point is earned for the curve that levels off to a relatively horizontal slope through the half equivalence point. So right, it's gonna level off. Like sometimes they'll start kind of steep, but it gets kind of flat through here. 1 point is earned for a relatively steep negative slope as you go through the equivalence point. At the equivalence point, that line really becomes quite vertical. We saw that in the pictures a minute ago. So anyway, there's 3 points there in that little graph, which to me, not too bad. Okay, so KW and water. Take a second and look at your formula sheet. KW is on there. KW is equal to the hydrogen ion concentration times the hydroxide ion concentration. And it's equal to 1 times 10 to the negative 14. This is why the pH scale goes to 14 and why pH, I forgot what I was saying there. Oh, pH plus POH has to equal 14. Like that's why it's all coming back to this, okay? So as temperature increases, the pH of pure water decreases. I did this math last week. I will do it again for you here in a second. But here's the deal. As I increase the temperature, your KW is actually where it is. There it is. So this is what's on the formula sheet, and they have an extra digit here. But as I increase the temperature, you can actually see that the KW is increasing. Did you see that? Yeah. So here's the deal. So I'm just going to put in some numbers. They're way bigger, but just for mathematical purposes, I'm trying to help you out, okay? So at 25 degrees Celsius, this is 10 to the negative 7th, and this is 10 to the negative 7th. You feeling me so far? Mm-hmm. Now, as I heat this up, what's going to end up happening, if you think about it, here is the ionization of water, right? You have this whole reversible reaction going on. KW is really small, so you have mostly products at equilibrium, right? But as I heat water up, this reaction is endothermic, okay? So if I heat this up, my pH is dropping. It's still neutral. These still have to equal. But what's happening is these ions, because if I heat it up, equilibrium is going to shift to the right. These ion concentrations are getting larger. So it's not going to get this large, but just for illustrative purposes, this, if it goes to 10 to the 6, and this goes to 10 to the negative 6, and this goes to 10 to the negative 6, the pH at that point would be 6, because that's the negative log of the hydrogen ion concentration. Because this number is going up, the pH is going to be going down, but it's still neutral. These are still equal, but pH is a negative log of this. pH doesn't have to be 7 at neutral. It is just where they're equal. How you feeling? Confused? What part confused you?
I thought they both had to equal 14.
Me too.
At 25 degrees Celsius, they gotta equal 14.
Wait, what did you just say? You said pH, like the statement you made before you.
pH doesn't have to be 7 at neutral. When we're looking at hydrogen ion, hydroxide ion concentrations, they have to be equal to be neutral. That is what neutral is. So listen, on your formula sheet, it has that. It says Kw equals hydrogen hydroxide at 25 degrees Celsius. Y'all know, and I'll sing you the song again. Only temperature changes. When you change temperature, the K changes. They're not going to add up to 14 if you're not at 25 degrees Celsius. Okay? How do you feel? In this situation, I mean, if we really, I don't even know if you can heat it up that much, but Kw would be equal to 1 times 10 to the negative 12th here. And pH plus pOH would have to equal 12. How's your math doing?
You can heat it up where it's like 6, right? pH. Maybe.
Yeah, actually, at 100 degrees. So yeah, I mean, you can keep going. But, you know, liquid water above 100,
You have to have some weird pressure.
you'd have to have increased it, but then that's, you know, then you're really changing some stuff. So I don't know if you can really get to 6. That's above my pay grade. Do y'all understand that as you heat up water, the pH goes down, but it always is going to be neutral? All right. Moving on with my life. Yay! Here's an example for our question for you. This is a multiple choice, so I'm going to give you until like 11:13 or 1:13. Thank God it's not 11:13. I'm out.
Yeah.
This one should be pretty quick for you. It shouldn't need that much time. I love you, but no. See, some people still thinking them. Do you recall that of the binary acids that are halogenated, right? Hydrofluoric acid is the only weak one because the electronegativity of the fluorine and the small size of that ion prevents water from deprotonating the acid, right? Okay, because really to this become the fluoride ion, the water has to be able to remove that hydrogen ion, but the fluorine is going to be pulling on it way too hard. The Coulomb attraction will be too high because the size is too small. Okay, anyway, at the equivalence point of titration, what would be the pH? Here's the thing. We're starting out with a weak acid, so our pH would actually be greater than 7. Got it? Yay! Okay. Here is more stuff for you. Vinegar, acetic acid. Now, is this a strong acid? No. Can you use concentration for pH?
No.
What do you have to make? It is.
Oh my god. I was trying to do an ice table on the strong acid.
The strong acids do not need an ice table.
I don't. Fine.
Let's see, let's just do this first question. I'm going to give you until about 1:16. You're not titrating anything. Number 1 is asking for the pH of a solution.
Oh,
Give you until 1:17. Do you want to go ahead and I'll give you until 1:18. You can go ahead and do the second one. I've told you how to do the number 2 like 1,000 times. So go ahead and do them both. This would be like part A of a free response. One little part of it, yeah. But this isn't an actual one. But they do this quite often. I need to learn how to fix my face.
Excuse me, it's very nice.
You got 2 more minutes.
I got 2.5.
Oh no, guys.
I'm gonna tell you what he does. You may not want to.
Oh.
Time's up. Love you. All right, look. Here's the deal. I recommend just making an ice table so that the way you do things stays consistent. When you have, like, if you're struggling this much with acid-base stuff and you're just like, I can't even keep this straight, I'm saying just do the same thing every time and then you don't have to worry about it. If you have a weak acid, to find the pH of a weak acid, if you do this ice table every single time, you know what it's always going to be? X squared over the concentration of the acid. And it's always going to be X squared over the initial concentration. If you can't even keep straight what we do, I'm going to say don't memorize a formula that's not on the formula sheet and just do what you know how to do. That's how I feel about it. And sometimes they ask other questions, and it may be helpful to have the ice table. All right, so anyway, if we look here, what they're doing, and this is really hard to see, but they have X squared over 0.5. You can ignore the minus X. They made an ice table, which I like. Yay. And then X, they actually use a quadratic formula. Not necessary. You can ignore the X. You can always ignore the minus X there. So I don't actually see what they got for X here. But the pH ends up being 2.5. Do I need to continue solving out for X?
It says negative log is 0.003.
Oh, okay, so 0.003. So X equals point. Oh, it gets bigger. Awesome.
Oh.
That's
Go
like
to the next slide.
goes to the next slide. I was like, yes, I did it. X equals 0.003. Okay. I'm gonna go home now. Anyway, X equals 0.003. And now when you get X, please remember that you're not done. X, you're not in math class. Once you find X, do we ever just solve for X in here? Like ever, honest to God, do we ever do that? When you find X, you're not in math, you're not done. So X equals 0.003. And so now you have to put 0.003 into the pH formula. And so pH is equal to, I'm going to hit this pen button. This X, 0.003, is your hydrogen ion concentration. And pH is equal to the negative log of the hydrogen ion concentration. So you have to put this number right here, hit negative log 0.003, hit the enter button, and there you go. Got it? You get 2.5. How you feeling? I would be willing to bet money that somewhere on the FRQ you try to find the pH of a weak acid. Like, that's going to happen to you. Alright? So on this next one, let me go back and see. Okay, here's the deal. Anytime you have an acid-base reaction, the strong acid and the strong base will both be on the same side. Do you remember me saying that to you over and over and over again? So anyway, you remember? Okay, So, good. I don't like how that got kind of covered up. Let me go back. There we go. So in this situation, the strongest base is obviously a hydroxide, and then the strongest acid is your NH4. So, there you go. I'm out. Okay, so how to do acid-base reaction species. This is where you're drawing particulates that show, we did work like this. I made you do work like this, and people still hate it, and that's okay. So here we go again. When we're doing titrations, this is a weak acid. So in solution before titration, most of your in solution before titration, your acids will be mostly protonated. They won't be deprotonated yet. So you have the whole molecule, including the hydrogen. This is the hydrogen that gets deprotonated, the one connected to the red one, the oxygen. Water's not gonna come along and like steal the hydrogen from an intramolecular covalent bond. Like that, no. I'm glad you laughed. Like that shows you understand things. Good for you. So here you go. So the starting before titration, here's my acid molecules. Now, at half equivalence, at half equivalence, so let me get the exact number. It's 50 milliliters, so at 25 milliliters, there's half equivalence. pH is equal to pKa. So if I wanted to find the specific pH, I would just put the negative log of the Ka they gave me. Because they'll give you the Ka of a weak acid, they got you. Yeah? So that's a thing. Anyway, half of my acid will be neutralized, right? And so here you go, or deprotonated. I shouldn't say neutral. That's not. I renege. Anyway, half of my acid will be deprotonated, and the other, this one's deprotonated, and the other one will still be protonated. Now, if this was a strong acid, then I would have, it would have started out with the hydronium ions making H3O, but this one's a weak acid. So, anyway, this one's been deprotonated. What they're not showing, they use sodium hydroxide. So there's a water molecule with the hydroxide. Let me show you. So this sodium right here was sodium hydroxide. So it came in with the OH, right? This hydrogen, let's just say it's this one, is right here now. So in this, not shown in this picture, is a water molecule that was formed. Okay, one hydroxide and one hydrogen ion made one water molecule. Okay, so anyway, at equivalence, all I have is the conjugate base. All I have here then, these two guys, these are my conjugate bases, my CH3COO1 minus. Okay, and I'm going to have two water molecules, and I have two sodiums as the spectator ions. They're not doing anything. They're the conjugate acids of the sodium hydroxide. They're not going to affect pH because they're a conjugate acid of a strong base. Anyway, so I have no more at equivalence. You basically are going to have conjugate acids, conjugate base, and water. You will have no base no original base, no original acid. Do you understand what I'm saying? And that's why in this situation, if we're going to have a pH of 8 or a little above 8, because this weak acid, its conjugate base, my acetate ion here, is going to bring the pH up because it's a relatively strong base, okay? And then after equivalence, anything after equivalence, I'm going to have extra hydroxides that will remain hydroxides in solution. That is what's bringing the pH up above 8 here for neutralized. And so, and here's my sodiums from the sodium hydroxide that was used to titrate. How you feel? It's not really that bad. If you can keep in your mind that here I only have acid, here I only have base, and here I only have the conjugate acid, conjugate base, and water, you only have 3 species in solution right here. Water, conjugate acid, conjugate base. That's it. They're equivalent. So anything that you had that was the acid or the base made water. So if you can keep that straight, then just half it right here, and then add a little more hydroxide over here, you're good. Right? Maybe. Nobody likes particulate models.
Wait, so Keto model at equivalent is only like the salt.
Can you say that again?
So at equivalence, you said there's only like
the conjugate acid and the conjugate base of what you started with, and water, and that's it. So you have water and a salt, yes.
How's the pH not 7?
Because acetate is a strong base because acetic acid is a weak acid.
Yeah. So like that means that the OHs and H's.
No. If you wrote that reaction from, if you went down that little rabbit hole and wrote how acetate creates hydroxide ions in water, we don't need to go there, but yeah, that's,
Oh,
I see what you're saying. Lord help. What?
That's what, like,
Listen to me. What they'll say at that point in the question, they'll say insignificant quantities what are present.
Okay, yeah.
Listen, Christian just asked me a question. Listen, he just said, let me see if I don't think I can hit the back button to make it work, but at this point I have acetate, I have sodium. Sodium's not doing anything to the pH. We can agree on that, right? The acetate, yes. There is a reaction between acetate and water that is creating hydroxide ions in the solution. But on the AP exam, we'll say what is present in high concentrations. If you pick something that says hydroxide, they're going to think you don't understand that hydroxide is equal to hydrogen there and made water. Because it'll say in high concentrations or significant concentrations. I understand what you're saying, but that's not helpful right now. Yes?
So you'll never have a titrant and then you'll think you're titrating
What?
ever there, but
No. Whatever the two species you start with that are going into your reaction, they will be neutralized at this point. You will have their conjugate, acid conjugate base, and water. No hydroxide, no hydronium. It's none. Alright, how to build a buffer. Whee! Okay, the pH of a buffer is primarily determined by the pKa. Do y'all need help? You're explaining the thing that you said? It's not worth it. Okay, so the pH of a buffer is primarily determined by the pKa of the weak acid and the conjugate acid-base pair. What? This whole situation makes a lot more sense if you look back at the Henderson-Hasselbalch equation. That buffering region, that beginning, slow sloping area, that's where you're going to use the Henderson-Hasselbalch equation. So pH, right? Let me just write it in here. If you're buffering, this is your go-to. So if we're creating a buffer, this is our thing. So we want the pKa of the weak acid and the conjugate base pair. Now, notice I'm talking about a weak acid. Are we going to use a strong acid to make a buffer? No, that's why we're just going straight to weak, okay? And we'll get into that a little bit. So when both species in the conjugate acid-base pair have equal concentrations, if these are equal and that's equal to 1, the log of 1 is 0. pH will be equal to pKa. Okay? Choose a conjugate acid-base pair that has a pKa close to the pH you desire, because at half equivalence, they will be equal. Okay, so, and then you can fine tune from there. A buffer is only as effective as it is sufficient amounts of both members of the conjugate acid-base pair to allow equilibrium to shift or stress. So, if you wanted to design like a sodium, an acetic acid buffer, you would use sodium acetate and acetic acid. Then you'd have enough of them. Y'all are looking at me real sad. I can draw it out if I need to. Let me see if it shows it. Not really. Okay, I'll draw you a picture. So let's just say we were wanting to make an acetic acid buffer. Okay. I like this guy. I'm going to do the best I can. Or actually, let's just be a little simpler, okay? Let's make a hydrofluoric acid buffer. That's a weak acid, right? So if I put hydrofluoric acid in solution, the thing is, if I just put this in water and I want a buffer, it's going to resist pH changes from additional acid or base. In solution, though, what is mostly going to be present in the species? Yeah, which species? HF. So if I add more base, if I add some sodium hydroxide, that's great. These are going to react and make water, and then I'll have sodium and fluoride, and that will change the pH much. But what if I add some acid? What if I add some HCl? It would actually react with the fluoride and make hydrofluoric acid. HF, listen to me, this is an acid. This is not going to affect the pH unless it gets deprotonated, and it will stay mostly like this. So if I add acid, it will make HF and chloride, which is really cool. But how much H and F am I going to have if I just add this to water? Hardly none, because it's a weak acid. So what you have to do is you have to make a buffer with a weak acid and then the salt of its conjugate base. So to make a good buffer, I would need a hydrogen fluoride in water, but then I would also have to add some sodium fluoride. And then I would have more fluoride, because this is going to break down into sodium and fluoride. Then I will have more F to make to neutralize any added acid. So you have to use a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. And so these need to be of sufficient molarity. Like you want these two molarities, the molarity of the hydrofluoric acid and the molarity of the sodium fluoride would have to be equal so that it can resist changes from acid or base being added. And then in sufficient quantities to neutralize any added acid or base. So if you only have a weak acid, that's not going to buffer very well because it will only resist changes from added base. Again, HF, this little molecule in water, this is not going to lower the pH. The pH is the negative log of hydrogen ion concentration. And this is not a hydrogen ion. It would have to get deprotonated first. That's the idea. So if I'm making more of these, it doesn't change the pH. How do you feel about that? Is that,
That's kind
do you want me to start over? Like what
well,
part?
it's because we have two acids.
I'm super confused.
Explain what a buffer.
Yeah, I just buffer in general. I'm confused, like why?
We forgot it. It's only at a certain pH.
But why would you need to do that?
So you
Well, okay, your body's blood is a buffer system. It's a bicarbonate buffer system. If your pH gets too high or low, the chemical reactions that rely on catalysts, the catalyst will get denatured and you will die. Okay, so that's why you need a buffer. In a chemical reaction, if you're a chemical engineer and you're doing chemical reactions for money, if the pH gets too high or low, then that's going to affect how much product you can make. So you need to keep the pH at a specific amount. Also, eye wash is a buffer solution. In case you get an acid in your eyeballs, you need something that will neutralize that, or a base. So, but a lot of eye wash stations have a buffer solution because if you go to the eye wash station, you have no idea, beforehand if you're going to get acid or base in your eye. A buffer solution is a solution that resists changes from an acid or a base.
So why do we have
It's
two
basically
acids?
like either.
Okay, when you say why do we have two acids, what are you referring?
HF and HCl.
I'm saying this is my acid I actually have. I'm saying if I need to buffer the pH, if I introduce HCl into this solution, the HCl is not in the buffer. I'm saying if I add HCl to the buffer, the fluoride ion will react with the hydrogen ion from the HCl and make HF, and I'll have a chloride. The purpose of a buffer is I'm going to add an acid or base and the pH can't change. So I got to add an acid in this picture so you can understand
it's
that.
just trying to, okay.
Yeah, and so if I come over here now and I add HCl, and I have something for it to react to.
So it's trying to make.
Make species
Yeah, so
that
they're
don't
not-
affect the pH.
Okay, so they're trying to basically.
Yeah, and you gotta remember, like a change in pH is an increase by a power of 10 for hydrogen ions or hydroxide ions. Okay. we're not done with this. I mean, there's a little bit more to it. I have some better pictures for buffers if y'all want after we're finished. All right, moving on. All right, check it out. Here's a buffer. This is the buffering. Can I help y'all? I don't mind. Do you have a question? Okay, so this is the buffering area. So this is where you'd use the Henderson-Hasselbalch formula. Again, this would, you would want to go POH and PKB and all that because you're starting with the base. Right? Okay, so be careful there. This is your PKB equals POH, right? Yeah. And it could still be PKA equals pH, but if you start with the base, that's not going to work. Anyway, your equivalence is at 25 millimeters, and so your half equivalence is at 12 and a half. That's not super crazy. Okay. This, if you're asked a question about a buffer, you look at the Henderson-Hasselbalch and you do a little mental math. This is actually one of the test questions from my test that you took. So it's pretty common sense if you look at the formula. You guys got it?
Yeah.
I'm going to write the formula down and then I'll go over it. Hi. These kind of questions honestly are kind of common sense. So if you want a buffer with a pH of 6.2 from an acid whose pKa is 6.5, this is 6.5, this is 6.2. Do you still like the answer that you picked?
Yes.
So I need to bring down this pH. What would I need more of? The acid or the conjugate base? The acid, that's all it is. So if I'm making a buffer, strong acid and strong base is not the right answer because you're not going to have species in solution that will neutralize added acids or bases in large quantities. So you want to have more HA than your conjugate base. So D is the best answer. Whee. Is that coming back a little bit now? Okay. Yay! What's in solution? Ha ha ha. If you have trouble with this, draw it out and think about your pictures. That's what I'm going to do when I explain it in a minute. I'll give you 2 minutes. Like I said, draw it out if you need to. It's okay. Let me ask you a question. Is concentrated to have equivalence? Does it matter the molarities or the volumes that you start with? No. Love you. Does it really matter the pKa in this situation? No, it doesn't. No, don't look, don't look, don't look. I'm quit my job. This pen is killing me. I heard somebody say pay attention. That's funny. Okay. Y'all ready? Look, if you struggle with this, start out with 2 of the molecules of whatever you're titrating. And so since it's a weak acid, I'm going to just draw it out all protonated, okay? Half equivalence means that half of these are going to be neutralized. So I need 1 sodium hydroxide. So I'm just going to put 1 sodium hydroxide. So I'm just going to do a swirly in a, I don't know, checkerboard. There we go. So the hydroxide, let's just make this OH. What's going to happen is this OH will make a water. So I have 1 water. I have 1 sodium. Okay. I'll have 1 acetate. And I'll have 1 acid. That's all you got to do. And then look at your picture you drew. So what's going to be the correct ranking of molarities of the species in solution? So I had 1 of these. I have 1 of these. I have 1 of these. And water isn't going to have a concentration in solution. I'll have, guess how many hydroxides I'm going to have in solution? None. Every bit of hydroxide added will go into neutralizing the acid until you get to equivalence point. None. So the smallest one would be hydroxide. The smallest one would be hydroxide.
Wow.
Alright, so these are equal. Yeah. So it's just B, which you already knew was the answer. But look, do you think I'm going to answer this question just like off the top of my head? No, I'm going to draw a little picture. Why don't you do the same thing?
Why is the H larger than
Because this is a weak acid, there will be some hydronium ions that are dissociated from the weak acid. There's no hydroxide.
because they're all going towards
Yes, yes. So that's a good question. Why is there some hydroxide? Because this is a weak acid. There's a bunch of it. It's not all neutralized. So in very small concentrations, you will have some deprotonated acid because it is a weak acid, but they still do break down some. Okay, good question. All right, here's the buffer mechanism. This is what I was trying to explain earlier. Why don't we go ahead and take a little break for about 15 minutes, and then we'll come back to this. we go, sweet. Let me unmute this. Whee! And we're off. Have you uploaded them? Yes. Check my channel. There you go. Alright, let's finish up this PowerPoint. Buffers. I just taught you this in advance because I wanted you to understand what was going on. A buffer is able to resist pH change because two components, the conjugate acid and the conjugate base, are both present in appreciable amounts. This appreciable amount point is why we have to add a salt. Not like hitting somebody, but a salt, an ionic compound that contains the conjugate acid or conjugate base, depending on the buffer that you're building. So then they'll be able to neutralize small amounts of other acids and bases in the form of H3O or OH when they're added to the solution. Take, for example, a fluoride buffer. A fluoride buffer will be made from hydrofluoric acid and NaF. An ideal fluoride buffer would contain, this is key here, equal molar amounts. You want to have equal acid and base of HF and NaF. Again, the F minus, it's not your grade, it is the conjugate base, which will react with any acids that you add in. Since they are a weak acid and a weak base respectively, the amount of hydrolysis is minimal. What that means is as they won't ionize in the water to create too many hydroniums or hydroxides themselves, which is what affects pH. Anyway, and both buffer species are present effectively at their initial supply concentration because they don't break down. They don't deprotonate. They don't ionize. So if a strong acid is added to the HF or F minus buffer, so the fluoride buffer, then the added acid will react completely with available base. This results in a nearly unchanged hydronium ion concentration and a nearly unchanged pH. So again, if I add into this fluoride, the fluoride is going to react to added acid. What they're going to do in the AP exam, they'll say in a fluoride buffer solution, you add hydrochloric acid. Show the net ionic equation for what occurs in the solution. The net ionic equation I'm going with is H plus F minus gives you HF. Do not spend time writing water and hydronium. But that's the net ionic equation that is occurring, and they will ask you to do that. Can I explain that to you? Alright, so it's saying if you add in some acid, okay, in this situation, if I added acid, the fluoride ion will be what reacts with the acid. The HF ain't going to react with the acid. They're both acids. That all makes sense. So anyway, the fluoride ion will react with the added acid. What I would do, what I'm telling you, for my net ionic equation, I'm going to write H-O. Sorry, sweet children. I'll do better. Everybody saw KSP and said, I'm out. I'll do better with my life. Anyway, no, I don't know what the problem is. I have broken my computer. Looks like we gotta go home. I really can't get it to come back up. Hello? There it is. I found it. I'm not sure what happened. I apologize. Oh, no, I don't want to do that. Oh my gosh.
What did you do?
I don't know what I did, and I'm sorry. I'm really sorry I did it, whatever I did. I'm going to go back to that screen. I'm going to talk to my deity, and hopefully when I start writing, it won't go crazy. There you go. I feel like we were here. What I was trying, I'm just going to prick my finger and write it in blood, okay? What I was trying to tell you. Okay, there we go. The net ionic equation, they may say some hydrochloric acid is added to this fluoride buffer solution. Write the net ionic equation for the neutralization of this acid. Like that's what they're going to ask you, okay? So it would be H plus F minus gives you HF. And those are all aqueous, so I didn't write that. But I'm not going to take the time for all this and all this. Do not do that. This is not a good idea. All the formulas on the form sheet don't even have H3O, do they? No, they just have H. Do yourself a favor. Anyway, if you add a strong base, what's going to happen? What's the net ionic equation for what occurs that keeps the pH from changing in the addition of a strong base? It may say something like that, okay? So in this situation, I'm going to have my HF, and so I'm going to add my OH, and I will get F minus and water. In this situation, you would have to write the water because you can't get out of it. You got an oath there, just having a party. Okay. How do you feel? It's good. Okay. So in this situation, the acid isn't really neutralized. It just forms a HF molecule. But the base here is actually neutralized. And then this is the conjugate base of a weak acid. But, you know, if you're already starting with a sodium, fluoride, and hydrofluoric acid solution, you're just making more F's, right? So that's not really going to affect the pH that much. The slight shift in pH after changing is governed by the hydrolysis equilibrium of HF. So this is what I was telling you, based on the new HF and F in concentration. So hydrofluoric acid plus water gives you fluoride and hydronium. And again, if this was me, I'm just going to go HF, aqueous, which implies it's in water. You don't need to write the water. It gives me H plus and F minus, both aqueous, okay? That's how buffers work. All right? You feel a little bit better about the buffers. All right, good. Here is you a question to do. Take about a minute. It really didn't really take a minute. Got it?
Not yet.
Okay, so of course, what is going to react with the hydrogen ion from the, or hydrogen proton from the HCl is going to be the fluoride, and that will make HF. So there you go. Good, good, good. Okay, KSP. When you have a KSP problem, anything actually with a capital K, you need to make yourself an ice table. KSP is the equilibrium solubility product constant. You don't need to know all those words. KSP is not on the formula sheet, but it's an equilibrium expression just like anything else. I kind of wish that this had some content before they threw the question up, but let's just talk about what you might need to know. If you recall, when you make the ice table for KSP, you're going to use the letter S. S is the molar solubility, which is the moles per liter that can be dissolved. So, what is the maximum number of moles of silver bromide with a full dissolve in 1 liter of water if the KSP value is 4.0 times 10 to the negative second? 12. Just kidding. You got this. Listen, you got this. You make an ice table. You know KSP, okay? And then you can solve. I believe in you. Make an ice table and go for it. I believe I can fly. Just kidding. In this situation, you're kind of lucky because your ice table is molarity, but you know your moles are going to be equal to your molarity because your volume is 1 liter. I'm going to go ahead and start this process up here. I can't make a tiny little cube. There, I did the best I could. right, did you get this far? What does S mean? It is the molar solubility of that species. So S is going to be the molar solubility of silver bromide. When you find S, that will tell you the number of moles per liter of silver bromide that will dissolve. That is what S means, right? So, here to solve for S, to take the square root of both sides is necessary. So, the square root of 4 is 2, and then we take the square root of an exponent that's basically the same as multiplying it by half. So, I got 2 times 10 to the negative 6. That's S. S is equal to the molar solubility, which is the maximum number of moles. So, the answer is D. Is that really that bad? No, you have to make an obstacle. That's all.
Wow.
Not put solids in it? Yes, when you do KSP, solids don't count. You're scaring me.
No, I did that. No,
Oh, okay. So you didn't do it today.
When we came back from Thanksgiving break after that week.
Yeah.
That's the Monday.
Oh, that was rough. All right. Using a conductivity meter and a pH probe, a student determined the molar solubility of a saturated solution made by dissolving hydroxide salts in water. This just sounds like they had such fun. A student's data is shown in the table above. There's your compounds. There's your solubility. Which of the hydroxide salts has the smallest KSP value? Here's the deal. If it wasn't for this mess right here, you could just say that, looking at just the solubility, what's going on. But you can't because you don't have the same number of ions, do you? I'm going to give you, I mean, that's a big difference. That's a pretty huge difference.
The power.
Yeah.
Yeah, that's statistically significant. I think you're probably good not to do math here.
Yeah.
Do you see why? Okay, first of all, do you see why we can't just look at this data and go, oh, okay, this one has the high solubility. If this had a 2 here, then you could just look. But if it's not exactly the same number of ions, like if it doesn't have 2 ions it dissociates into or 3, they're not all the same, you can't just look at KSP or the amount that dissolves. You can't, oh, this is the molar solubility. This is S.
Mm-hmm.
Oh, so you can't just look at it. You can't just look at KSP. Someone's making that way too hard. The solubility is S. You can compare S's to S's all day. You cannot compare KSPs unless you have the same number of ions it dissociates into. This one's going to make 2, but the chromium hydroxide, chromium 3 hydroxide, this is actually going to break down into 4 ions. But S, this solubility is your molar solubility. And if you get like moss, I just saw it because it says moles per liter, and I'm like, oh, that's the S. So anyway, this is actually a pretty quick question. Yes, sir.
Wait, it's solubility in the table, but it's asking you to compare KSP. So can you still just compare them?
So you're gonna have to fill.
You have to multiply.
Because
You would have to fill it back into the
Okay.
You'd have to fill back into the KSP expression.
Okay, that's
Yeah,
fine.
good question. So yeah, so you have to compare the KSP values. So since you have S, you'll be able to fill that back in. I don't know if you don't necessarily need, when you have 2 ions, the equation is 4, 2 of them is S squared, 3 is 4S cubed, but then this one, you may need to write it out to see what it becomes, you know what I'm saying? Like write out the ionization of chromium 3 hydroxide. But anyway, get yourself some KSP expressions, fill in S, and see what happens. I'm going to give you maybe about 5 minutes, so maybe until like 2:19.
Yeah. This is one of the ones that probably take you a little
It
longer.
is a multiple choice question, but it is one that you need about 4 or 5 minutes for. And to me, it almost looks like a FRQ.
It's
You
like
know?
those long tapes, multiple choices.
But y'all know some of the multiple choices are, some of them are like that. I'm not going to write anything. I'm actually gonna rewrite that. Is it coming back to you now? I hope so. We're almost out of time. Alright, did you fill numbers in? Alright, look. If there's two ions, like silver, bromide, that will break down into silver and bromide. Then it's S squared is KSP. After that, I would take the time to write down an ice table and make sure I'm not screwing up. That's just my preference and my opinion. Now, for this chromium 3 hydroxide, here's your KSP expression. There's your S. You're going to fill it in. Now, if this is multiple choice, okay, which it is, S, that 27 ain't really helping you. I mean, I know that's pretty difficult because you don't have a calculator. You're going to have something to the 4 times something. I mean, yeah, you're going to have to raise to the power 8 or negative 8. So your exponent in this situation for KSP is going to be something around 10 to the negative 32nd. I mean, I'm estimating, but that's what you're doing. You don't have a calculator. All right? For this one, this is basically 1 times 10 to the negative 1, right? So if I put that into 4s cubed, when I cube it, I'm multiplying exponent. So this is going to be real close to 10 to the negative 3rd. This is 1 times 10 to the negative 2nd. When I cube it, it's going to be real close to 10 to the negative 6th. This one right here, when I cube it, it's going to be close to 10 to the negative 27th. So if I have to rank them, which sometimes you do, the lowest, smallest KSP is going to be the chromium 3 hydroxide. But then this one, and then this one, and then this one. This really isn't so bad if you take the time to do the work.
So how does the thing not work? The little trick, the S trick.
The S trick.
I mean, it's like for 4 at least it does.
Well, when we did the work in class the other day, you had to know it was actually the concentrations at equilibrium. Do you remember that? Yes, I remember that. And I was like, this is why you need to know how to do it always. But having the formulas memorized for this situation is fine, but FRQs are not this easy. They go into craziness. They're like, when does precipitate form? That's the situation.
That's the KSP stuff that I
Don't like?
yeah.
Yeah, that's because you don't do it out the long way. But if you do, it's not that bad. All right, so here is the answers. So it's option C, and we did the math. Good times. And that's what I'm talking about. You don't get a calculator on that multiple choice, so you need to know that when you raise a power to a power, you multiply them. Common ion effect. So the solubility of a sparingly soluble hydroxide or anything can be greatly increased, or for this question, or comment. This solubility of a sparingly soluble hydroxide can be greatly increased by the addition of an acid. So, for example, the hydroxide, magnesium hydroxide, is relatively insoluble. The reason it's insoluble while something like barium hydroxide is a strong base is because barium's ionic radius is much larger than magnesium's ionic radius. So the Coulombic attraction between the magnesium and hydroxide is too large for the hydroxide to be removed and the base to be ionized. Do you recall this? Okay, good. So when an acid is added to the saturated solution, remember I told you this, if you add a strong acid, even if this is a weak base, which it is, it does not matter. The acid will come in and react with that hydroxide. It doesn't matter if it's a strong base or a weak base. It does not matter. It will still react to the same magnitude because hydrogen plus hydroxide has a huge K value, right? Yeah. Okay, so anyway, KSP is given here. When acid is added to that saturated solution that contains excess solid magnesium hydroxide, the following reaction occurs and removes hydroxide from solution. So they'll often do Le Chatelier's kind of questions where they'll say, what will adding an acid to this solution do to the reaction? Right? If I add acid, it's going to react with the hydroxide, and then this will become more soluble as the reaction shifts toward the product to replenish the hydroxide that was neutralized by the acid. So that's a stretch, but you got to be able to do it. So as more acid is added to a suspension, the equilibrium shown in 18.7.7 is driven to the right. I guess that's this. So more dissolves. In contrast, the solubility of a sparingly soluble salt may be decreased. Now this is the common ion effect. That is not the common ion effect. That is the Le Chatelier thing. The common ion effect, if I come in here and let's say I add some sodium hydroxide, then I'm going to have too many hydroxides or more hydroxides. So actually shift back to the magnesium hydroxide to take the hydroxide out of solution. So, or if I add magnesium chloride, which is what they're giving me, another common ion will be the magnesium ion, more will precipitate out. More magnesium hydroxide will precipitate out, and it will reduce the solubility. So that's this common ion effect. It's kind of like Le Chatelier with ions. That's all it is. Okay. All right, here you go. This is a real quick one. For a solution equimolar in hydrocyanic acid and sodium cyanide, that would be a perfect buffer solution. This would be a cyanide buffer solution because hydrocyanic acid is a weak acid. And so I have to see how I can look at that and see. Anyway. Got it? Not yet? Okay. All right, that should be enough time. So which one is false? So the hydrogen ion concentration is larger than it would be if only hydrocyanic acid was in solution. Do I need to I think I may need to write, if it was me taking this test, you know what the first thing I would have done is? Write it out. So, let me pick the pen button. No. Ah! I'm trying so hard. Come here, pen. There we go. So let's look at what that looks like. So about HCN, and that's going to break down into plus CN, right, I ran out of room, the hydrogen ion concentration is larger than it would be. No, let me tell you why. When I add sodium cyanide, it's going to ionize into sodium and to cyanide. So I'm adding a common ion, which is going to shift the equilibrium back to the left and make more HCN. And I just put up the comment about it being a perfect buckler because it is, okay? And you should be able to look at it and see that since we already discussed it. All right, so when salts dissolve, we kind of talked about this already. The enthalpy of dissolution is dependent upon the intermolecular forces. So do you know how we talked about breaking bonds is always endothermic and then forming new bonds is always exothermic? Well, dissolving an ionic compound is always going to be endothermic because you're going to have to break down the lattice energy, the energy that's holding the ions together. And then you're always going to release energy when the water surrounds the ions. Now, if I have something like, I'm trying to think, maybe I have some examples here of dissolving certain, I don't think they do. But yeah, this is the energy needed to separate them and then the energy released when the solution is made. And so some of them, if I mix two things together, I'm trying to think of something that's endothermic and exothermic. I'm so sad that I can't. If I mix two things together and it's exothermic and the beaker gets warmer, then more energy was released when the water surrounded the solute and the ion dipole interactions kind of were formed. What's funny? Oh, thank you so much. You guys, those little spitter things. If I'm mixing two things together and it's endothermic, that means, it feels cooler and the temperature drops. That means that more energy went into breaking apart the lattice than was released when the water surrounded the ions. And that pulled energy from the water, and that's why the temperature dropped. That's all this is showing. How you feel about that? All right. So, in general, when I dissolve a salt, entropy increases. But there are some situations where I don't even want to talk about it. Anyway, entropy increases. So Gibbs free energy, K, and I feel like we already did this a lot.
We don't need to know this.
No, you didn't know, but we already did it a
We
lot.
don't need this
No.
slide.
All right, so that's the end of the content. So what we have here is we have some more problems, and then we'll go into, yeah.
It's okay. It's okay. Next slide.
No, do you not get it? It said
No, I know. No, I made the PowerPoint. Yes, I get it. I made the joke.
No, them. They were all like.
No, I get it. I can't see the reaction. I'll have to look it up and show it to you. Let's see. No, this is the FRQ that you need to do.
Alright, this should be enough time. So which one
My
is
phone's talking to me. That was weird. Okay, so why don't we go ahead and look at this one, Ron, and I'll write the equation for you at the top. It is, I say I'm going to write the equation at the top for you. We'll see. It is, you guys okay back there?
No.
What's that?
It is 2 iron, 3 oxide, 2 of those, plus 3 sulfuric acids. And that's going to yield iron sulfate plus 6 waters. And this is aqueous. This is aqueous, and that's aqueous. Alright, so this is a really good practice FRQ that my friend wrote for fun. He's
He's a nerd.
a nerd. He has a PhD in biochemistry. He is a nerd, yes. Thanks, Russ. So I'm going to give you about 20 minutes to cook on this. It's a great practice for Monday, and then we'll go into the lab work. So take until 2:50. symbols are just aqueous signs, and I'm not very good at writing little with the pen. If you can't see the board, you can come around and look at my computer screen. I completely invite you to do that. I've never read Harry Potter. I feel like I'm missing out. You haven't read it either? I'm not a true nerd. What? Even though this is cute, these are actually like real legit things for to think about with the experiments. Like where could enthalpy get changed and stuff. It's good. Can we hit the button? Are you ready to go?
No, I'm talking about one.
Oh, the air conditioner button. We have too many buttons. I don't know. I'm always hot when I'm teaching because it makes me nervous. Actually, no, my
Q is
That's why I told you it is.
Well, I have to be sure it's really annoying. Last year, it was the day before my AC exam, and I was able to
This is the day before the kid exam.
yeah, but I
when
want
the
Have y'all?
yeah, he doesn't.
I put extras.
He doesn't.
I think it is. I think it is that.
But he doesn't. He's still taking
He said, like, she said till 10:30 for the ACE exam, and I said you could catch me outside leaving.
Why'd you take them out?
I say no to it.
Make sure you can handle C. Right, that's fun.
No, it's alright.
Which part?
B for I, assume that Ron would actually do it on versus
How would you expect her temperature change to differ from Ron's? For this comparison, assume that Ron's reaction would perform with the lid on. Oh, what he's saying is assume that she did it like that, like versus the way he actually did it. Because he didn't do his with the lid on, did he?
No, so wouldn't that be the difference? But it's the same assuming he did.
I think on I you have to compare what she did to what he did.
No, she's
No, she got more than those.
Oh.
He is 45.
She got the lid on.
No, she's got.
But if there's more liquid, so that's it. There's more liquid.
That's a lot more.
Yeah. And we did a problem like that the other day. Remember? No. Okay, here's the deal. The liquid doesn't matter for Q.
Okay.
But the temperature change, the more liquid is going to reduce the temperature change. Because you got to remember, Q is equal to all this stuff multiplied together. Well, if the mass is bigger, then that temperature is going to be smaller.
What?
I'm so glad.
Lord help. Q equals mass times specific heat times temperature.
Yeah.
That specific heat is not changing. So if Q is equal to the same thing because you have the same moles reacting, then the temperature change is going to be smaller if the mass is bigger because they're multiplied together to give you that same constant.
I'll tell you, explain
Dude,
it.
just write it on the board. It's like easier to visualize probably that way.
Well, we're not done yet, and I'll do it then.
Well, Purple's just gonna be lost.
Purple, I'll come over.
So,
I'm coming over. What I'm saying is, if you have more liquid, then that mass is going to be tiny. Q for both of them, if you have the same moles reacting, it's going to be the same. If you have a bigger mass, the temperature change is going to be smaller. Math is fun.
it's not saying it has
No.
Yes.
Is it saying that
All your
Q is the same?
milliliters.
So, okay.
Then that would have to be the same.
Yes, the aluminum hydroxide is not.
No, we're just talking about B two.
Aluminum.
Yeah, so it's saying,
So it's like you're increasing all those values.
but they're using gram, they're not using pressure, so would you want to like, would your because they're not using, I didn't get what you're saying, but I'm saying they're not using grams.
It'd be grams.
They're using grams.
I guess I didn't put it in.
I understand what you mean. Like,
I think the iron 3 hydroxide mathematically is a limiting reactant.
Yeah.
So it didn't change the enthalpy because your moles of reactant didn't change. So the enthalpy release wouldn't be any different. But I'm talking to him about the
Nicoscope.
about the temperature change thing. Because the iron 3 hydroxide is the limiting
Then
reactant.
it just wouldn't change.
Oh, so it is.
Because
I
this
don't know.
temperature change is not Q.
Oh, yeah.
Their temperature change would be less because the mass of the solution is higher. Yeah, that's the math thing I was just talking to you and I walked over there.
But it's not saying Q is the same for both.
Okay, but if the iron 3 hydroxide is a limiting reactant, yeah, the Q is going to be the same. The heat release will be the same because the heat is formed by that reaction.
I get it. Can't do it.
I enjoy this so much.
So it's not so it has a diluting reaction.
Iron hydroxide, if you make a BCA table, which you probably should, I mean, for this situation.
I was gonna say,
I mean,
you
but-
can see if it to see if it is diluting reaction.
Right, that's what I'm saying.
If it is, then it must be.
Right, and then, but is it when you do?
I don't know.
I don't think anybody down
Yeah, I was about to.
Okay, and then C. So like 2 would be like B2, so it would have to be greater temperature change, right?
Wait, B2?
Yeah, aluminum weighs less than.
It's
Oh,
always,
yeah,
it
it's
would
not
always be
used,
greater,
right?
it would always be greater if,
The
I don't think
safety
you never-
capacity is the exact same thing called.
The temperature change would have to be greater.
Aluminum
This
hydroxide.
value is
Oh,
also.
well, okay.
Right?
To have the same moles of aluminum hydroxide, your mass would be less.
Yeah,
So
so
your
and
mass would have, it would have a larger temperature change because the mass
to
is
make this
less.
A larger temperature.
Because the mass of 1 mole of aluminum hydroxide is less.
oh, that makes sense.
What's capacity you're using in that, like, whenever you're talking about Q, and this 15 stays the same, like, what the current
Of the solution. And they would give you the specific heat capacity. Oh, they did.
Wait, for B2, is it saying that the temperature would be different?
Yes, because the okay, if the enthalpy of the reaction is the same, then Q is equal to mass. But here's the thing: a mole of aluminum hydroxide weighs less than a mole of iron 3 hydroxide, man. So that mass is less. So if Q stays the same, but temperature's got to be bigger when you multiply them together to get the same number.
But it didn't say, but it said all the measurements, all the same measurements.
I know, but you're using aluminum hydroxide, so the mass of everything altogether is going to be less because 1 mole of aluminum hydroxide weighs less than 1 mole of iron 3 hydroxide. Look at the periodic table. Aluminum weighs 26, iron weighs 55.
I understand.
But they're
why
not
I was
using
thinking that. I was
45
thinking the
grams.
grams stayed the same. In the
No, the grams are the grams of solution. You add up everything, and that's your mass. That's the mass of the solution. So the mass is going to be less because the iron 3, the aluminum hydroxide weighs less.
So even though they told you 45 grams of iron hydroxide, not moles in the beginning,
Hang
so
on.
wouldn't they just use 45 grams of aluminum?
Let's see.
Because in B they say 45 grams of iron hydroxide, not like whatever moles. I get it if it was 1 mole of iron hydroxide compared to 1 mole.
So if you use 45, okay, so if you use, the heat would actually be greater then because you'd have more moles of the hydroxide. So Callie is saying if you had 45 grams of each, your mass wouldn't change, but you'd actually have more moles of reactant, and that was your limiting, so you'd actually release more heat.
But if you're doing the Q, then it's just mass, it's not moles.
So the mass doesn't change, but the overall energy, the Q itself,
Oh, because
that's based on the reaction that occurs, and you'd have more moles of reactant, which would make more heat.
so much.
I know. It's okay. I think we're. Y'all ready to talk about this?
Yes.
Everybody's like, yes.
Miss Freeman,
Yes.
okay, we're going to see a movie, where are we going? Like the movie what?
How do you say it?
What's the T word, the movie? Like,
Title?
it's a giant building in which movies are shown.
What do you say?
Theater.
Theater.
Theater? For theater, for theater.
I don't know. It depends on who I'm talking to. I fancy it.
What are your code switching?
Let me ask. Yes. Did y'all do part C?
Can
you do part C? Lord, just
I got this.
try part C. Did you do part C yet?
I don't know if I did it right, but I got the sulfuric acid.
Part C is given entropies. If you don't know what to do, guess what you should do? Go to moles. Can you go to moles? Nope. When in doubt, mole it out. And then put it on ice. Is ice table going to help you? And then check the formula sheet twice.
Talking about C?
Yeah.
You should do the entropy of the products minus the reactants.
Yeah, I know. That's what I'm saying. But people don't know what to do. I'm trying to help you.
What are you talking about?
We should
I'm still stuck on the first part. You said that iron 300 oxide was the limiting reactant.
But you'd have to do a BCA table to actually find out. I'm saying if it
That's
is.
what I'm doing.
Okay.
I don't think it is.
You don't think it is? Okay. Okay. There's a formula for it.
Yeah, okay.
I think if you do a BCA table, I think the acid may be the limiting reactant. Did you? You have to. I think before you do anything, you know, if you didn't start by doing that, you should have done that. Do y'all need me to work that out and show you how to do the BCA table to find the limiting reactant? No. What? It doesn't, but any kind of stoichiometry problem, you don't know anything unless you know the limiting reactant. You can't do anything. Because you won't know which one's like limiting the amount of enthalpy release. Part C, you don't need a limiting reactant. No. We're gonna go. Yes, thank you.
That's like the things we spend in solutions.
Say again. Are we going on a field trip? No.
Like, pretty, good job.
Let's go on a field trip Monday.
You're going on a field trip to the test on Monday. I wish you well.
I am too.
That went right past my head. Why are y'all doing that?
I'm gonna be this Wednesday.
This is the first part of grade.
Wait.
This is exam work.
Does it have to leave it?
All right, come on, part C. That one's really straightforward. Still got to do the lab component. And then I wanted to reteach you electrochemistry just real quick. Not funny, I'm sorry.
No, that's the thing. Either I'm doing something wrong or a lot of people.
All right, I'm giving it till 2:50. All right, sweet children. So the first question says, what other information would Ron need to know in order to experimentally determine the molar change in enthalpy of the reaction? He would need to know what the limiting reactant was, because that is going to determine how many moles of products are made. Do you see what I'm saying? So if you don't determine the limiting reactant before you start, the rest of the questions you cannot intelligently answer. You won't know how it's going to check the enthalpy, affect the enthalpy that's formed, because you won't know if adding more of the product, or excuse me, reaction will make more products and make more heat. Yes.
You also don't have temperature change.
You have to measure the temperature?
Yeah, true. But I think that they both matter. You really would you would need that too. I mean, I have the answer key, but that's the thing. On the second part, unbeknownst to Ron, Draco dropped a 100-gram sneakoscope. This kind of thing on number 2, they ask about a lot on the AP exam. So because the sneakoscope would absorb heat, the heat of the reaction that you would actually get when you did the calculations would be lower than you would expect. Did you all get that one right? Good. So even if you're doing all these questions, you don't know the first part, you'll know some of it. So don't worry. On part B, Hermione, is that how do you?
Oh my God.
I don't know. I've never seen Harry Potter.
I haven't
Never even heard.
Hermione. I gotta go.
All right, time out. whoever she is, mixed 45 grams.
It's a boy.
No, it says 3 later.
Why are you assuming his gender?
No, it says 3 later on in the question.
Alright, she mixed 45 grams of iron 3 hydroxide with 450 milliliters of 2 molar sulfuric acid in her cauldron and kept the lid on using a spell to measure the temperature. Okay? So, how would you expect her temperature change to differ from Ron's at all? For this comparison, assume that Ron's reaction was performed with the lid on with no stethoscope. So, if you do the math again, like you have to do the math again, and in her situation, the iron 3 hydroxide is the limiting reactant. So what you do is make a BCA table, do the moles, find X. You know how to do that, but I don't think you did. But that's what you would have to do. Yes.
Right on these, we would need to show like.
And I don't think they would make you do it that much work, but you would have to know the enthalpy change. Otherwise, if you just mix extra of something that was already excess, it will not change the temperature because no more reaction will go through. Yes.
On 2, you said it was lower, right?
Yeah.
Why?
Because energy is being absorbed by whatever thing he was talking about.
The
More,
stethoscope.
she has 400.
Oh, wait.
Oh, number 2.
On- On this one, on I,
Yes.
yes, Captain. On I, Captain. The stethoscope would absorb heat, so that would be less heat that you would actually be able to.
But,
Yes.
But
But
if you
you
do
add-
it in the formula
adding
context,
mass.
wouldn't it be a bigger mass?
He says that she doesn't know.
No.
Doesn't know it's in there.
He doesn't add the mass to it.
It does. They don't know what's in there. So you're taking the temperature, right, to calculate the heat change, or the enthalpy change. But you don't know that thing is in there and it's absorbing energy that is not going into the water or the
Okay.
solution.
But even though he doesn't know it, like actually, would it go up?
But he's doing the experiment, so
But I'm just asking, like, for me, like, would it? Like,
no,
actually?
the temperature change with it in there versus not in there, the temperature change would be less because it's absorbing heat.
Even though the mass is greater, like you wouldn't get a greater Q.
So what is the specific heat capacity of this thing? It is absorbing some heat. So yeah, it would be less. All right. So on B, I forgot what I was talking about. Oh, if you do the math again, excuse me, the iron 3 hydroxide is now the limiting reactant, and so her temperature change. If you look at it, you have to compare. Yeah, because she added more sulfuric acid. As far as this one goes, they have. Here's what they have. They have there are more moles of reaction if you do the BCA table, right? And so that would decrease the temperature change, the exact same delta T outcome increase. Okay, so
The sulfuric acid.
there's a significant increase in the mass. So you have to do a lot of legwork in here to specifically compare them. Don't stress out. You're fine.
In the first part, the sulfuric acid is
The first one and the second one was the iron 3 hydroxide. If you do the math again, so you'd have to do some math to determine the limiting reactants. I think we learned that lesson here. On part C, did you guys get this?
I didn't even get to it, but probably.
If you got to it, did you get that? All right, good. Let's go over the labs. All right, so the labs. This is kind of fun. Gravimetric analysis. We did a gravimetric analysis. You mix two solutions together. You make a precipitate and you filter it out, and then you can come back and determine the identity of one of your solutions and the molarity of it. So percent composition, empirical formulas. You can dehydrate a hydrate, which is where we heat up the hydrate. Any of these things, look, if it's any of, you take something and you're trying to find it. If you're trying to find a formula, we spent a lot of time on that last Saturday. You go to moles, divide by the smallest one, and get a whole number ratio by multiplying by whatever number you need to do. Do you remember what I'm talking about? Present to mass, mass to mole, divide by small, multiply to whole. That is your answer, pretty much for anything to this tune. Okay. So what you're going to do is you're going to mix your two solutions together. You're going to get your precipitate, your lead sulfate here, lead 2 sulfate, and then you're going to filter it, and you're going to weigh the solid lead 2 sulfate after you dry it repeatedly. Okay, and you dry it, and the mass remains constant. So possible sources of error. If you have contamination in a solid, that would make your measured mass too large because the contaminants would be massed in with your precipitate. Okay? They're going to ask you about sources of error, and those are your easy points, so you need to make sure you're comfortable with this. Incomplete precipitation, so if some of the ions went through the filtrate, and it would go through the filter paper, that would make your mass too small. And then if the solid did not get fully dehydrated, like if you didn't repeatedly dry it and mass it until the mass was constant, that would make your measured mass too large. Gasol labs, we did this. Here is the little car thing. Do you remember with the fusion of gases? We talked about the molar mass of the molar masses of gas. If they're at the same temperature, then the higher the molar mass of the gas, the lower its velocity will be, because it's like kinetic energy is equal to the half. There's a little formula. It has mass and volume in it. Do you understand that like a heavier object, with the same amount of energy will go slower? So anyway, NH3 has a mass of like 17, but HCl has a mass of like 38 or 36. And so the NH4Cl will actually form closer to the HCl because the HCl will not be traveling as fast as the ammonia. Okay, so there's that. We did, I don't know if I did this for you, I did it last year. Remember, Drew? That was fun. Can I do it for you guys too? We talked about it with little cars. Alright, so there's your PIP nerd. Listen, a lot of times with your Gasol labs, or Gasol things, those are really easy. Fill it in, whatever. Make sure you go to Kelvin. But a lot of times they'll ask for molar mass. Don't let that freak you out. Molar mass is equal to grams per mole. So you get your moles. Molar mass is equal to grams per mole. I don't. Look, it's right, not right? Okay, fine. Grams per mole. We're always worried about this. We did this lab and we measured the volume of the gas that was formed, and we were able to go using the ideal gas law to moles, and that was fun. I enjoyed that lab.
We did do this.
Yes,
Yeah.
I'm talking about this down here, Graham's law, the fusion.
Sorry.
All right.
Thought I had.
So you just fill things into the ideal gas law. We did this lab. Here, look how cute this is. She did such a good job. Her gases get informed, and you have hydrogen gas, and you can measure the volume. Now, remember Dalton's law? When you're collecting gas over water, you have to subtract the vapor pressure of the gas, of the water, because Dalton's law is on your formula sheet. The pressure of all the gases is equal to the partial pressures of whatever gases are there. Total pressure is equal to partial pressures added up. Yay! So if you have an air bubble to start, your volume will also obviously be too high, and then your the volume would be too high. Okay, so here's your question. I wish you well. Take about a minute. Do you remember how to make a mole fraction? If you don't, it's on your formula sheet.
It's right there. That's dirty.
All right, I love y'all. I already got it. You got it?
Yeah.
All right, so the total pressure in here is 100 millimeters of mercury, and then, you have 1 mole of gas, right? So you have 0.25 moles of neon, so the partial pressure of neon is the total pressure times the mole fraction of neon, which is 0.25. It's basically, mole fraction ain't nothing but a percentage or proportion, right? No big deal. So the answer should just be A. Did I do it?
You did it at
Oh, okay. I was doing a percentage and I didn't. Okay, my fault. So it is C. I'm just kidding. Thank you so much. All right, chromatography is where we're going to separate out a mixture into its components. We're going to be able to do that using intermolecular forces or differences between intermolecular forces. So we already kind of talked about how this actually works. there's a thing called column chromatography. Your adsorbent packed into a glass column, and then the solvent moves down slowly, and it makes little fractions. I don't know if they would go into that very much. Yeah. So what you're doing is you start out with a mixture, and you here's your mixture, and you're constantly adding your solvent, and your solvent will, it's the same thing. The solvent will carry what has the most common intermolecular forces with it farther down. That's all. It's not a big deal. Yeah, it's not a big deal. Click if you need to watch a video that's there. Incomplete separation, overloading. All right, synthesis. We didn't, I don't know if we did anything with synthesizing anything like alum. I don't think we did. Y'all remember the formula for percent yield? Actual divided by theoretical times percent at, yes. So they may ask you to look at theoretical yield versus your actual yield. So how you would do this, how you would synthesize alum. So your source of aluminum is reacted with potassium hydroxide, and you would end up getting alum at the end. You mix it, heat it, recrystallize it, and then this is going to be that same thing where you're doing moles and being able to determine how much you form. Doing the filtration, make sure it's dry, no problem. Titration with acids and bases. Remember whatever your is in your burette. You need to, it's your titrant, and then your analytes what's down here. Remember when you read a burette, burettes are to the first decimal place, so when you read the measurement on a burette, y'all, this right here, this is actually, I mean, it's right at 0, but if, let's just pretend this was like 1.0. We would actually have to call this 1.00 because it goes to the nearest tenth, and then you have to guess that next one. Remember, significant figures, you'll all know what's one estimated. And then your strength of your graphs. So this is a strong acid base because it's at 7. Right here, I'm starting with a weak acid. Yeah. And then here, this is 1, 2. This is a diprotic acid, and this is a it's a base like I don't know what to call it. It's not a diprotic, but it's the base that breaks down twice. So they have sodium carbonate. I don't see a whole lot of that happening, but anyway, you have those multiple equivalence points. I wonder if they have a special name, I'm wondering. So titration, you can use phenolphthalein, that's the nice little pink one. It's a wrong assumption to think that the endpoint is the same as the equivalence point. So, you know, you could overshoot the endpoint, not reading the bottom of the meniscus, and, you know, not reading it accurately. Here is your question based on acid-base titration. Should be pretty straightforward. It should be that fast. I love you. Got it? Yep. So it's just E, right? Because after the equivalence point, your pH is just going to really be determined by the added acid. Did you get this one, or did you get it backwards? Because this is a base getting titrated with the acid. Did you get it? All right, good. Good for you. Redox titration, we talked about potassium permanganate and titrating it. You can also use potassium dichromate. Potassium permanganate is its own indicator because once it finishes reacting and there's nothing left in your beaker to react with, it will leave the solution pink. So I don't know if they would test that specific stuff. But redox titrations are happening among redox reaction. Acid-base titrations, there's no electrons transferred. You have a proton getting transferred, but if you do the oxidation numbers, there's no change in oxidation numbers when you have acid-base. Nothing changes, I'm sure. Anyway, in redox titrations, the species react with oxidation reduction. Some redox species act as self-indicators, like I said, potassium permanganate. And redox titrations are commonly seen with D-block elements that can have the multiple charges, and they form like coordinate complexes, and we didn't really get into that, but anyway, I guess you can use a volt. That would be cool. You can use a voltmeter to determine what's happening with the redox reaction. We're not that high tech. Or a redox indicator. Iodine, in the presence of starch. I think this is backwards. Iodine indicates this presence of starch. That's backwards, but I mean that's what happens there. All right, kinetics. A lot of people use crystal violet. I told y'all about that. As the reaction goes through, it turns colorless. Do you have a question, Andrew? No? Okay, I'll help you. So clock reactions, those are iodine based and they turn clear. Our friend Nick did one last year. It was pretty cool. Remember with the data plot, we can already tell that this is a first order reaction because this is molarity versus time. This is natural log of the molarity versus time, and this is 1 over the molarity versus time, the one that makes a straight line. And that's really common kind of FRQ. Yes?
Is there gonna be stuff about like galvanic cells? Because we didn't really go.
There wasn't the PowerPoint yet, but yeah, we definitely need to. I gotcha. It's fine. Which of the following would increase the rate of a chemical reaction? This one's really straightforward. Got it?
Me too.
So probably D, decreasing the constant weight. Oh.
What?
That doesn't make sense. It's B. No wait, where is it? Oh, I read E and I was like, E's wrong. Yeah, it's D. It's totally right. That's perfect. Great. Calorimetry. I feel like we've talked about calorimetry a lot today. I think you're good on that. Flame test. You can determine, what substance you're talking about because each unique ionic compound, each unique metal has an individual color. But these aren't super accurate. You really need, spectroscopy to see, differences. Write this or not that. We've went over this a lot. I want to go over a few things here. Make sure that you make a choice. Don't just say changes. You have to say increase or decrease. And the same is true with the apes. If it changes that, no. You need to say increase or decrease. Be very specific and say which way. So answer specific questions first, then justify or explain. So make it easy. So do your math and then explain it. It's basically what they're saying. Species. So if you say it or stuff or whatever, species is a general term for any kind of chemical substance, and it could be a reactant or product. So the species reacts with blah, 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 instead of saying it. A justification or explanation when it is part of the question, only the answer without supporting it. So a lot of times it'll say, provide a calculation and justify your answer. So you do the math and then you write a sentence or two explaining, why it's backing up your point. The math is. Mass or volume, don't say size, that doesn't mean anything. Reference to specific data or graphs when prompted to explain how the data. Don't make generalizations without specifically citing provided data or trials. And so, obviously reference what they give you and be specific. Data-ionic equations only contain a species that change. So, aqueous ionic compounds and their dissociated forms. So don't include spectator ions. Just be really careful with that. So particle view diagrams. We did that a lot. Make sure your dipoles point in the right direction. That's not a big deal for y'all. And answer with units if includes units as stated in the problem. If it says include units, you need to make sure your answer has the units. That's sometimes a point. Show work used to derive an answer. Not showing the work. Show your work. Answers expressed to the correct number of significant figures. Make sure that you're doing that. And there will be 1 point from that, and you should be lab-based. Gases, components of the kinetic molecular theory. So ideal gas law. So that doesn't always work. So values with correct signs. Make sure when you're doing calorimetry, ask yourself, what is the system doing? What are the surroundings doing? And you may put the sign right most of the time. K with units. So remember how to find the units of K. You look at the overall order, subtract 1, then flip the sign. This is third order. The units of K would be molarity. 3 minus 2 is 2, negative 2. Molarity, negative 2, seconds, negative 1. They're always seconds, negative 1. Do you remember what I'm talking about? Okay, so if it's 0 order, then it would be 0 minus 1 is negative 1. Wait, did I get that wrong? Yeah, so it's molarity and then S negative 1. So you subtract 1 and then flip the sign.
No, the 0 order is just seconds.
I think first order is just at seconds negative.
Yeah.
Seconds negative one's first order. I think I'm right.
So zero order
Is M negative 1. No.
Zero, M, subtract it, you get negative 1.
Wait, no, I think zero.
Make it positive, so it's M S.
Yeah. What? Yes. And I said that a second ago.
Okay, yeah.
You subtract 1, flip the sign, S negative 1. And that works for all of them, I'm sure. Okay, so make sure you have the units going on. A rate law that includes the rate constant K. So remember, rate is equal to K, and then your concentrations raised to the exponents determined experimentally, not the coefficients. Rate law only on the reactants. So rate laws don't generally include the products. Q versus K. Look. You cannot say reduce the stress or due to Le Chatelier's principle. You cannot do this. So I didn't make this slide. Somebody that is a reader did. Okay? You have to say Q versus K. I think I made my point today. Proceeds. So shift. If equilibrium has not already been established, like saying shift may not work for you. KSP expressions, they should only contain the ions. They shouldn't have the solid. KP. Remember it's big P and then the species. And we did that today. You know what I'm talking about? Be careful there. X is small relative to the original concentrations that it can be ignored. So you have to, make sure you say that X is small enough to be ignored. So,
Wait, we have to say that?
I would, if it was me in my ice table, I would circle X and I would say small enough to be ignored. That's what I would do, which I did in class over and over again. With acids and bases, pH is greater than 7 because the salt produced in the neutralization reacts as base. pH is greater than 7 because it's a battle. Don't personify stuff. It wants electrons, they fight. No. Don't do that. By the way, that whole it wants a full octet to be like the noble gases. You know that you're gonna have to go back to net effective nuclear charge and then Coulomb contraction, all that kind of stuff. Kw equals Ka times Kb for a conjugate pair. So, for example, HF and F minus, the Ka for HF times the Kb for F minus equals Kw. Did you know that? Did you remember that?
Can you repeat that right?
A conjugate acid-base pair is equal to Kw. So the Ka for HF times the Kb for F minus equals 1 times 10 to the negative 14. So if we had
Oh, yeah.
that's been a hot minute. I didn't go over that. So if you had something like, I don't know, acetic acid, like the Ka for acetic acid times the Kb for acetate will equal 1 times 10 to the negative. Now they have to be like little pairs, conjugate acid and base pair. Acid and a conjugate base pair. They're not like the same species that was deprotonated. Like you can't do that. pH is equal to pKa only at the midway. What is the half equivalence? So effective nuclear charge increases. Look, you cannot say it wants to have a full octet. It is so close to having a full octet. That does not ever work. You need to effective nuclear charge increases, and so it'll be able to ionize, whatever it's removing the electron from. Okay. It has more polarizable cloud of electrons. It has, we only say it has more electrons, so it's more polarizable. That's okay. But don't just say it just has more electrons, more mass, it's bigger, it has more protons. No. You have to say both, and we did that over and over again. Period. Shell. They want period. Okay. So. What? Elements are in a period. Electrons are in a shell. So if they're talking about elements in the third period, you shouldn't say elements in the third shell. Is what it's saying. Okay.
Have we ever said that?
No, but people do, I guess. Reference reasons for periodic trends, effective nuclear charge, Coulomb's laws, polarizability. Just don't say because it's on the lab, because it's further down the periodic table. You're not that. Electrons in higher energy levels are farther from the nucleus, resulting in a larger atom. More electrons make it bigger. So the number of energy levels is the reason why. And you can say more shells, that's okay. Oh my gosh. So if you want to change phases, you're overcoming intermolecular forces. You're not just breaking them up. What does that mean? Are you breaking bonds? That's too vague. Coulombic attraction? Don't say opposites. Look, if you don't know nothing else, you know about some Coulombic attraction.
It wants us to say it. Violent interactions.
Opposites.
Describe the process of overcoming intermolecular forces. I already told you can't do that mess. It has hydrogen bonds between the molecules, has hydrogen bonds. So the thing is, it's really common for people to think hydrogen bonds are the same as intramolecular bonds, like a covalent bond. So hydrogen bonds between the molecules. That doesn't take but a second to write the extra word. Yes.
It doesn't want us just to say LDFs.
We're talking about ion.
Wait, am I there yet?
No,
Yeah,
you're skipping
Where?
The second.
discussing.
This one?
Number
One above
2.
it.
LDFs are not in ionic compounds because they're not polarizable. They're in a lattice. What's moving around? Nothing. Thanks. Sorry. Ions. Make sure that if it's an ionic compound, it's an ion. If it's not an ionic compound, you have to call it an atom. I feel like I just okay, yeah. Lewis structures that are complete with necessary lone pairs. So a lot of times people, because they're so used to drawing the skeletal structure, like we'll leave off the lone pairs. So make sure everybody has a full octet. We did that today. Count your formal charge up. You're fine. Identify specific intermolecular forces. Don't just say stronger ones. Dissolve when discussing interactions between molecular substances in a solution. So if hexane can't dissolve in water, then you shouldn't say hexane cannot ionize in water. That does no. Like acetone, this is a better one. Like ethanol can dissolve in water because it hydrogen bonds with water, and so you can't say that it ionizes in water like salt does. But it's a molecule. But you're looking at me like that would be dumb, but you'd be surprised.
You can't say dissociate.
It doesn't. Dissociate means to break up. Does ethanol
that's
break
what
up?
I meant.
So it attacks. Apparently, that's a thing. Loss of mass of electrode is due to atoms of electron going to solution. We talked about how galvanic cells worked. I feel like y'all need me to do that again. They were giving me that eyeball about that a minute ago. When the electrode actually loses mass, it's because the electrons are lost to the wire, but then those metal atoms become ions and go into solution. I feel like I'm going to need to draw it for it. When I finish this, I will. Discussion of Q versus K for changes in cell potential. With the galvanic cells, which I'm about to do, you can't talk about Le Chatelier because they're not at equilibrium. A battery's not equilibrium because of cell potential will be 0. So you have to use Q versus K. So if you know that voltage is going to increase, then Q is less than K. If you know that voltage would decrease because of a change, Q is greater than K. You have to make that. You cannot say anything about shifting otherwise. Alright, so I'm finished. I'm bidding the people on the internet to do, and I'm going to reteach you some galvanic cells. People on the internet, I cannot teach you galvanic cells. I guess I could.
No.
No.
I don't like being watched.
You don't like being watched. I have copyrighted material that I teach from, so I'm sorry. Stop streaming.